Hello there, and welcome to Science for Sleep, where curiosity settles in beside you, and the universe becomes a little quieter, a little more patient, and maybe even a little more comforting as you drift toward rest. Tonight, we're taking a slow and steady walk toward one of the most extraordinary discoveries of our time, something that began as a distant point in the sky and gradually revealed itself as a gateway into the deepest questions we've ever asked. It's a place where light strains to escape, where gravity becomes almost unimaginable, and where our understanding of the cosmos shifted in a single moment when an image appeared that many people thought humanity might never see. This evening, as you get comfortable and your mind settles at its own pace, we're going to spend time with M87, the black hole that changed everything. I'd like to ease you into the story the same way the universe eased us into this discovery, not with urgency or pressure, but with small steps, familiar details, and simple questions that help your thoughts slow down. Before we dive too far into this immense subject, I'd love to know where you're listening from tonight. Maybe you're at home, tucked into a comfortable spot. Maybe you're unwinding after a long day. Or maybe you're already half asleep and letting these words carry your attention just enough to keep you company. Whatever the case, take a moment to notice the time where you are. Is it late evening? Early morning? One of those in-between hours where the world feels a bit quieter than usual? There's something fitting about settling into a calm space while exploring something as massive and distant as a supermassive black hole. If this gentle journey brings you even a bit of calm, or if learning about the universe helps you unwind as you're getting ready for sleep, I'd be grateful if you gave the video a like or subscribed. It helps this quiet little corner of the internet reach others who might need a soft place to rest their thoughts. And as always, take your time with this. Let your breathing fall into a natural rhythm and let your mind wander as much or as little as it wants. There's no rush and no expectation, just a slow path through a fascinating part of the universe. Now, as we turn toward the centre of this topic, imagine that somewhere far beyond the haze of city lights, beyond the thin layer of atmosphere cradling our planet, and beyond the familiar constellations you might recognise from childhood, there sits a galaxy called Messier 87. It's large, ancient, and brimming with activity. It contains stars by the trillions, clouds of gas stretching for thousands of light years, and clusters of material that have been swirling and evolving for billions of years. And at the centre of that galaxy sits something so heavy, so compact, and so powerful that for a long time we weren't even certain if it could truly exist in the form we imagined it. Yet there it was, waiting beyond our reach until technology finally caught up with our curiosity. But before we get to that moment when the first image appeared, it helps to understand how this subject gradually approached us over time. Black holes didn't start as dramatic scientific truths. They began as mathematical possibilities long before we could measure them or observe them directly. They were hypotheses, thoughts on paper, ideas that came out of equations about gravity and motion. They were treated cautiously from a distance, sometimes skeptically. The universe is full of things we imagine long before we confirm, and this was one of the biggest examples of that. As scientists studied the heavens, they began noticing certain signs: stars moving too quickly near invisible centres, gas swirling in patterns that hinted at an unseen force, jets of matter blasting outward from galaxies at incredible speeds, as if something deep inside them were twisting space itself. These clues came slowly over the years, building upon each other until the picture began to form. Something massive was hiding in plain sight at the heart of many galaxies, and one of the most dramatic examples was in M87. The story of how we reached the point of capturing an image of that black hole is full of small human moments. Countless nights spent in observatories, computer simulations that ran for weeks, discussions that stretched long into early morning hours, adjustments, recalibrations, tests, doubts, and breakthroughs. And underneath all of that was something both simple and extremely human, a desire to understand something larger than ourselves, a desire to see what had never been seen. Even before the first telescopes joined together to form a planet-wide array, people were already fascinated by what could be sitting at the centre of M87. The galaxy itself had been photographed countless times by amateur astronomers, professional researchers, and large observatories. It's a bright elliptical galaxy, easily recognised by the immense jet of material shooting out from its core. Even before we had detailed measurements, that jet suggested something extraordinary was happening in the centre. The power required to launch matter across thousands of light years at speeds approaching light itself was beyond anything ordinary. It required something capable of bending space, controlling energy, and influencing entire regions of the galaxy. That alone made M87 a subject of great curiosity. Yet even then, the idea of actually seeing the black hole's silhouette was considered nearly impossible. The object is 55 million light-years away. Its event horizon, though enormous compared to smaller black holes, still appears tiny when seen from here. Trying to capture it with a single telescope would be like trying to photograph a grain of sand on a distant beach using a camera the size of your hand. It wasn't feasible with conventional methods, but science often finds ways to make the improbable possible. As we walk slowly into this story, it helps to take a moment to think about just how patient the universe has been with us. The light we eventually captured near the event horizon had been travelling across space for tens of millions of years. Long before humans existed, long before Earth had its current continents, long before early mammals took their first steps, that light left the region surrounding M87's black hole and made its slow journey through intergalactic space. By the time it reached us, our species had developed technology capable of recording it. The timing wasn't intentional, of course, but coincidences like this remind us how remarkable it is that we're able to observe anything at all given the scale of the cosmos. You might be wondering why this one black hole in particular became such an important target. After all, black holes exist throughout the universe. Our own Milky Way has one at its centre. The answer comes down to a combination of size, distance, and clarity. M87's black hole is massive, billions of times the mass of our Sun, which means its event horizon is large enough to resolve with a global telescope network. And unlike our own galaxy's centre, which is filled with dust and gas that obscure our view, M87's surroundings are comparatively cleaner, giving us a clearer path to its silhouette. It's as if the universe placed a spotlight on it, inviting us to take a closer look. This quiet journey we're taking isn't only about the black hole itself. It's also about the people who dedicated years to studying it, the gradual unfolding of ideas, and the way a single image changed the way millions of people think about the universe. Sometimes a discovery affects only a small circle of researchers. M87 was different. When its image was revealed, it crossed boundaries. It reached people who had never been interested in astronomy, people who had never thought much about physics, people who saw a glowing ring on a screen and felt something shift inside them. The universe felt a little closer, a little more real, and a little more connected to our everyday lives. As you continue listening, let yourself settle into a comfortable rhythm. There's a lot to explore, but nothing needs to be rushed or pushed forward. Just let each moment pass naturally. If your eyes feel heavy, that's perfectly fine. If your attention drifts, you can always return whenever you're ready. The story will keep going, moving steadily through the science and the history and the small details that build toward understanding. Right now, we've only taken the first steps. We've met M87 from a distance. We've acknowledged the strange and powerful object hidden at its centre. We've glanced at the decades of clues that brought us to this point, but this is just the beginning. If you let your attention drift gently from the story of how we first approached this distant object, it's easy to picture the region of the sky where it lives. Somewhere beyond the familiar constellations you might notice during an evening walk, there lies a cluster of galaxies known as the Virgo cluster. It's one of the nearest large collections of galaxies to our own, a kind of cosmic neighbourhood where hundreds of galaxies gather, each one containing immense populations of stars. And nestled deep within that cluster sits a galaxy that stands out not because it is the brightest or the most colourful, but because of its size, its age, and the extraordinary activity happening at its core. That galaxy is M87. M87 is one of the giants among galaxies. It's not shaped like the graceful spirals you might see on posters or screensavers. Instead, it's a huge elliptical galaxy, round and smooth when viewed from a distance, without the swirling arms or patchy dust lanes that make spiral galaxies so visually intricate. This gives it a deceptively simple appearance. If you didn't know any better, you might think it's just a soft glowing sphere of stars. But the simplicity hides an enormous scale. M87 contains more stars than our Milky Way by a considerable amount. Trillions of stars packed into a space so vast that even a beam of light would need tens of thousands of years to cross it. And yet, from our perspective on Earth, it sits quietly in the background of the night sky, without a hint of how large it truly is. As you get more comfortable, you might picture how this galaxy has been forming and evolving over billions of years. Unlike some galaxies that move through space with elegant, well-defined shapes, M87 looks like the end result of countless mergers. Smaller galaxies collided with it long ago, their stars swallowed up and spread throughout its expanding form. Over time, these collisions created the round, featureless outline we see today. The galaxy didn't grow in a neat, organised pattern. It expanded through the steady accumulation of everything that drifted into its gravitational reach. Long before humans existed, long before Earth cooled enough to sustain life, M87 was already collecting the material that would make it the massive structure we observe now. If you imagine standing far outside the Virgo cluster, looking toward M87, you would see something that isn't immediately obvious from one image alone. This galaxy is bursting with activity. It emits light across nearly every wavelength scientists can measure. Radio waves, visible light, ultraviolet rays, X-rays, and more all reveal different parts of the galaxy's structure. These emissions tell us that something powerful is happening inside it, something that isn't occurring in most galaxies to such a dramatic degree, and that something is found at its centre. The centre of M87 is unlike most galactic centres we've studied. Many galaxies contain black holes in their cores, but the one in M87 is exceptional, both in size and in the amount of energy it produces indirectly through the matter swirling around it. If you let your mind settle on the idea of a black hole, you might picture something like a region of pure darkness. But around that dark region lies an enormous amount of gas and dust, heated to intense temperatures as it spirals inward. This material forms what scientists call an accretion flow, a swirling, glowing structure that emits vast amounts of radiation. In the case of M87, the accretion flow is so active that it affects the entire galaxy, influencing the way matter moves and how energy is distributed. One of the most striking features associated with this galaxy is the jet that shoots out from its centre. Even if you've never spent much time looking at astrophotography, you might have come across images of M87's jet. It's a long, narrow beam of particles moving at speeds that approach the speed of light. It extends tens of thousands of light years from the galaxy's centre, like a straight line carved across space. This jet is not produced by the black hole itself, but rather by the complex interactions of magnetic fields and matter near the event horizon. Energy builds up and escapes in a focused beam that travels far beyond the region where it formed. When astronomers first discovered it in the early 20th century, it was unlike anything they had seen in other galaxies. If you've ever looked at a photo of M87, you might notice how the jet appears almost delicate from afar, as if it's a thin thread of light stretching across the galaxy. But this is a thread of extraordinary force. The particles inside it move at nearly the fastest speed anything can travel. For them, distances measured in light years pass in what feels like almost no time. The jet carries enormous amounts of energy, shaping the environment around it and influencing how gas clouds behave in that part of the Virgo cluster. Through observations across multiple wavelengths, scientists have been able to track how the jet expands, how it bends slightly as it moves outward, and how it changes in brightness over time. These measurements help us understand not just M87, but black holes in general. As you continue listening, it's helpful to remember that when astronomers study a galaxy like M87, they aren't just looking at a picture, they're looking across time. The light reaching Earth today left the galaxy roughly 55 million years ago. Back then, the continents on our planet were shaped differently. Early mammals were beginning to diversify. The climate was changing in ways that would eventually allow new ecosystems to form. The light continued its journey with no awareness of what it would encounter upon arrival. It simply travelled until humans built instruments sensitive enough to detect it. So when we say M87 is the giant at the centre of Virgo, we're describing not only its mass and size, but its presence in the immense history of the cosmos. Observing this galaxy has required using many different tools. Ground-based telescopes, space-based observatories, and radio telescopes have all contributed pieces to the puzzle. Each tool reveals a different layer of the galaxy. The visible light shows its broad structure and the glow of its stars. Radio waves reveal the jet and the activity near the core. X-rays show hot gas heated by interactions around the black hole. When combined, these observations give us a nearly complete portrait of the galaxy's behaviour. Scientists can follow the paths of high-energy particles, trace how gas moves in the central regions, and infer how much mass the black hole must contain to produce the effects we observe. Those effects are staggering. The black hole at the centre of M87 is believed to be billions of times more massive than our Sun. It's one of the largest black holes we've ever measured, and its mass influences the motion of stars far from the centre. Even stars located many thousands of light years away feel its pull. The sheer amount of material gathered in that region is hard to fathom. Yet despite its mass, the black hole itself is tiny compared to the galaxy. It occupies a region small in comparison to the distances between stars, but gravity doesn't need size to exert influence. The black hole's mass is concentrated into a volume so compact that space around it becomes warped in dramatic ways. This warping affects everything nearby, bending the paths of particles and shaping the flow of energy. You might imagine the central region of M87 as a place where matter moves according to rules very different from those that govern everyday life. The gas near the black hole orbits at speeds that would tear apart most structures we're familiar with. Temperatures reach heights far beyond anything naturally occurring on Earth. Magnetic fields twist and snap in ways that release enormous amounts of energy. And all of it is driven by a black hole that cannot be seen directly. What we observe is the behaviour of everything around it, the way matter responds to the intense gravitational environment it creates. It took decades for astronomers to develop the techniques needed to study this region with precision. When you look at M87 through a small telescope, you won't see much more than a soft oval of light. Even larger telescopes show little detail in visible wavelengths. The central region is too distant and too small to resolve clearly. That's why scientists turn to radio wavelengths, which allow us to peer into the structures around the black hole with far greater resolution. Radio waves can penetrate dust and gas that block visible light. They can be combined from telescopes around the world to create an image with remarkable clarity. This was the key to revealing the shadow of M87's black hole. But reaching that point required building a global network and coordinating observations across continents. The story of M87 as a giant at the centre of Virgo is not only a tale of astronomy, but also a tale of patience. The galaxy has existed for billions of years. The light from its core has been travelling for millions of years. The observations needed to study it took decades to refine, and the discovery that would eventually change how we view black holes happened only because countless pieces of this long story aligned. M87 waited for us. It sat quietly in the background of the night sky until we developed the tools needed to look at it closely. And when we did, we found something that exceeded even our boldest expectations. As you settle deeper into this journey, you may notice that understanding this galaxy doesn't require rushing. Each detail builds upon the next in a steady way. There's no need to frame it as a dramatic mystery or a cosmic puzzle, being solved in a moment of revelation. Instead, it's a gradual unfolding, much like the natural rhythm of night giving way to early dawn. M87 reveals itself piece by piece as we combine data from different wavelengths, compare theories to observations, and slowly refine our understanding. Even now, astronomers continue to study how the jet behaves. They track how bright it becomes, how its shape shifts, how the particles within it evolve. This long-term monitoring helps reveal the processes happening near the black hole. The more we observe, the more we learn about how galaxies like M87 function. Some of these discoveries confirm what we expected. Others challenge our assumptions and force us to re-examine old ideas. But every observation adds a bit more clarity, showing us how interconnected the galaxy's features truly are. The mass of M87, its structure, its jet, and its central black hole are all part of a larger story about how galaxies evolve. Some galaxies remain relatively calm over time. Others go through turbulent periods. M87 appears to have had a turbulent history, one shaped by mergers, gravitational interactions, and intense activity near its centre. Yet despite all of that, it has settled into a state where it appears stable on large scales, emitting light that helps astronomers trace its current state. When we look closely at the centre of M87, what we find is not just another black hole. It's something far more extreme, far more massive, and far more challenging to comprehend than the versions we used to picture in older science books or simple diagrams. For a long time, black holes were ideas more than realities. They appeared in equations and theorists wrote about them, but most of our early impressions came from imagination rather than observation. Small black holes formed from collapsing stars were the main kind people talked about, the kind that fit within a single thought or diagram without overwhelming the senses. But the object at the heart of M87 did not fit comfortably into those early imaginings. It was too big, too powerful, and too influential on its surroundings to be described by those simple pictures. The black hole in M87 is classified as a supermassive black hole, and that term isn't an exaggeration. It contains billions of times the mass of our Sun. Try, for a moment, to imagine something that massive all gathered into a region much smaller than the orbit of our solar system. The gravity is so intense that even the fastest particles cannot escape once they cross a certain boundary. And yet, we don't actually see the black hole itself. We see the effects it has on everything around it. This is what makes it so different from what early scientists visualized. Those early ideas imagined black holes as simple, isolated structures, but this one is part of a vast system. It draws in matter, heats it, compresses it, and accelerates it until it emits energy across the entire electromagnetic spectrum. The region near the black hole is not silent or static. It is filled with motion and heat. Gas doesn't fall straight in. Instead, it spirals around the black hole, forming a structure that moves at incredible speeds. The gas heats up to temperatures so high they exceed anything created naturally on Earth. The matter brightens in radio waves and other wavelengths, creating the glow that allowed us to form the first direct image of a black hole's shadow. Without that glowing material, we wouldn't have seen anything. The black hole would remain invisible, hidden from view no matter how powerful our instruments were. What makes this black hole unlike anything previously imagined is not only its mass, but the complexity of the environment around it. To understand why, consider how it interacts with magnetic fields. As matter orbits the black hole, it drags magnetic fields into tight tangled loops. These fields twist, stretch, and realign in ways that release enormous amounts of energy. The interactions are so powerful that they help launch the jet that shoots outward from the galaxy's core. Scientists used to think black holes simply swallowed matter and didn't do much else. but M87 shows that they can influence entire galaxies through these interactions. This swirling, energetic environment is sometimes described with numbers that don't quite register at first. Temperatures reaching billions of degrees, particles moving at a significant fraction of light speed, a region where gravity is so strong that time passes differently compared to places farther away. While all black holes share these characteristics, the scale here is what makes M87 so extraordinary. Its mass allows it to shape matter and energy far beyond the central region. Even stars several thousand light-years away feel its influence. If you lived in a solar system orbiting within M87, the gravitational pull of this black hole would be a fundamental part of the landscape of your night sky. For a long time, scientists tried to model such a black hole using equations and simulations, but even the most advanced models struggled to capture all the details. So much was happening at once, and the conditions near the event horizon were too extreme to replicate in any laboratory. The only way to truly understand what this black hole looked like was to observe it directly, or at least observe the material near it as clearly as possible. But observing it came with enormous difficulties. The region we needed to see was extremely small when viewed from Earth. Even though the black hole itself is billions of kilometers across, it appears tiny because of the immense distance. It's similar to trying to see a very small object on a distant hill. Even if the object itself is large, distance compresses it into a point almost too small to distinguish. To make things more challenging, the material around the black hole is constantly changing. The flow of matter shifts, the brightness fluctuates, magnetic fields rearrange themselves. Everything is in motion. Imagine trying to take a clear photograph of something that not only sits far away, but also changes shape and brightness over time. And even if you manage to photograph it, the limits of resolution mean the image may look blurry or incomplete. Yet despite these challenges, scientists pursued this black hole because it represented a kind of ultimate test. If we could see the shadow of the event horizon in M87, we could confirm predictions made by general relativity. We could observe how light behaves in extreme gravitational fields, and we could compare the image to the models developed over decades of research. As you soften your thoughts and let this story move at its own pace, it might help to picture what early scientists thought a black hole might look like. Some imagined it as a simple dark sphere surrounded by a faint halo of light. Others pictured swirling patterns or pure darkness without any surrounding glow. But what came out of M87 was far more structured. The black hole's shadow didn't appear as a simple circle. It showed a ring of light brighter on one side, dimmer on the other. That asymmetry came from the motion of material around the black hole. Gas moving toward us appears brighter because of the way light behaves in relativistic conditions, while gas moving away from us appears dimmer. This detail alone confirmed that the material was orbiting at incredible speeds, and that the gravitational field was warping the light around it. Before the image was captured, computer simulations predicted what we might see. These simulations used the equations of general relativity to trace how light would travel near a black hole. The model showed a bright ring surrounding a dark shadow. But predictions are never the same as direct observations. Many scientists wondered whether the real environment around M87's black hole might differ from the models. Perhaps the gas would be too turbulent. Perhaps the magnetic fields would distort the image. Perhaps the resolution of the telescopes would not be sharp enough. Many uncertainties lingered even as the Event Horizon telescope prepared to observe it. The moment the real image appeared, it was immediately clear that this black hole was not simply a theoretical construct. It was a physical object with a specific shape and behavior. Seeing the bright ring in the dark center confirmed decades of physics. It also showed details that expanded our understanding of black hole environments. Even something as simple as the thickness of the ring provided clues about the temperature, density, and motion of material near the event horizon. Scientists could compare these details with simulations and adjust their models accordingly. Another aspect that makes this black hole so different from what people imagined is its stability over long periods of time. Smaller black holes can change quickly, The matter around them varies from moment to moment, but M87's black hole, with its immense mass, moves at a slower pace. The structures near it evolve, but not so rapidly that we lose track of them. This stability gave scientists confidence that they could capture an image that represented more than a fleeting moment. The brightness around the black hole shifts, but the overall structure remains similar for extended periods. This made it an ideal target for the first image of an event horizon. As you let your breathing relax into whatever rhythm feels natural, you might notice how each part of this story builds on the last. Nothing about the environment near this black hole is simple. Everything is connected. The motion of the gas influences the brightness. The magnetic fields influence the motion. The mass of the black hole influences everything around it, and the light emitted from the material must navigate all of these influences before escaping into space and eventually reaching Earth. The path of each photon is shaped by the gravitational field. Some light bends around the black hole completely and returns to where it came from. Other light curves around partially, creating the structure that makes the ring visible. Some light falls inward and disappears entirely. What remains is a collection of light that shows the outline of the event horizon's shadow. This black hole also challenged earlier ideas about how jets form. For many years, scientists weren't entirely sure how black holes launched jets at nearly the speed of light. The magnetic fields near the event horizon seemed important, but the exact mechanism was unclear. Observing M87 helped clarify how the rotation of the black hole and the movement of matter combine to generate these jets. The black hole's spin plays a crucial role. As it rotates, it drags space around with it, twisting the magnetic fields and providing the energy needed to launch the particles. The jet from M87 helped confirm these ideas. Its structure, brightness and behaviour told scientists that magnetic fields were being tightly wound and accelerated by the environment near the black hole. Another feature that sets M87's black hole apart is its ability to influence its entire galaxy. In many galaxies, the central black hole is relatively quiet. It consumes matter slowly and doesn't produce large jets. But in M87, the black hole consumes matter at a rate that allows it to emit enormous amounts of energy indirectly. The jet delivers this energy to regions far outside the core, affecting how gas cools, how stars form, and how matter distributes itself across the galaxy. The black hole is not just a passive feature, it is an active participant in the galaxy's structure and evolution. Its presence shapes the environment in ways that scientists are still measuring and refining. Even now, after the first image of M87's black hole has been studied and analysed extensively, it continues to challenge our expectations. New data helps refine the details of the ring's brightness, thickness, and shape. These refinements help astronomers test general relativity in ways that were impossible before. Each small measurement helps us understand how matter behaves under the most extreme gravitational conditions in the universe. And these conditions cannot be recreated anywhere else. They exist only around black holes like this one. As you drift comfortably through this story, you may notice that the black hole doesn't feel like an isolated object anymore. It is part of a much larger system. The galaxy revolves around it. The jet extends from it. The gas flows into it and heats up near it. The magnetic fields twist because of it. And the light we capture from its surroundings tells a story that spans millions of years. It becomes clear that this black hole is not only unlike anything early scientists imagined, but also unlike anything that appears in simple explanations or diagrams. It is larger, more active, and more deeply connected to its galaxy than most people would expect. All of these qualities made it the perfect subject for an ambitious project like the Event Horizon Telescope. The idea of imaging a black hole's shadow had been discussed for decades. Many believed it would remain out of reach, but M87 provided an opportunity that was too extraordinary to ignore. Its size, brightness, and activity created the conditions needed to form a clear image. When the telescopes around the world synchronized and gathered data, they weren't just observing a distant object. They were observing a black hole that had the potential to confirm or challenge some of the most important theories in physics. Long before the image of M87's black hole appeared on screens around the world, long before telescopes were linked across continents, and long before computers could process mountains of data, there were hints scattered throughout the history of astronomy, small signals, unusual behaviours, unexplained motions that whispered of something massive hiding in the shadows of the universe. These clues didn't point to a clear picture at first. They didn't neatly tie together into a single explanation. Instead, they were fragments of information collected across decades, gradually forming a trail that scientists would follow with growing curiosity. As you let yourself settle into this part of the story, imagine the early days of astronomy, when scientists first began to measure the movements of stars with precision. They didn't have sophisticated instruments. They didn't have satellites orbiting Earth, or computers capable of running complex simulations. They had telescopes that were modest by today's standards, and their measurements were often recorded by hand. Yet even then, certain observations stood out. Stars near the centres of some galaxies moved too quickly. Gas clouds swirled with more force than expected. Something invisible seemed to be pulling on them, bending their paths and accelerating their motions. These hints weren't immediately connected to black holes. At the time, black holes were still theoretical concepts, mathematical solutions to equations written down by physicists trying to understand gravity. When researchers first encountered the idea that gravity could become so strong that nothing, not even light, could escape, the concept seemed extreme. Many scientists thought black holes were curiosities of theory rather than objects that could actually exist. So when astronomers saw stars moving in ways that didn't match ordinary explanations, they didn't jump to conclusions. Instead, they recorded the data, compared it to other systems, and tried to rule out more familiar causes. As the years went by, more of these unusual movements were detected. In different galaxies, stars near the centre behaved unpredictably, moving much faster than expected based on the mass that could be seen. The gravitational pull in those regions was too strong to be accounted for by visible stars alone. There had to be something there, something large, something compact, something that didn't emit light, but exerted enormous influence. These early clues formed the foundation for what would eventually become a strong case for supermassive black holes. But no single clue was enough on its own. Each observation had to be combined with many others to build a picture that made sense. The process resembled assembling a puzzle without knowing exactly what the finished image would look like. And for decades that puzzle remained incomplete. As radios and electronics advanced, astronomers discovered a new way to study the universe: radio astronomy. Suddenly the sky revealed features invisible in ordinary telescopes. Radio waves, unlike visible light, pass through gas clouds and dust that block other wavelengths. When scientists pointed radio telescopes toward the Virgo cluster, they detected a strong radio source coming from the direction of M87. This radio emission was much stronger than what would normally be expected from a galaxy's stars. Something near the centre was producing it, and not just producing it, but generating it at levels that suggested incredible energy. This was one of the most important hints. A quiet galaxy doesn't emit strong radio waves, but M87 did, and the signal pointed directly toward its core. As research continued, another clue emerged. Researchers discovered a jet of material extending outward from the centre of M87. This feature had actually been photographed in the early 1900s, but it wasn't well understood at the time. Photographic plates showed a faint streak coming from the galaxy's core, but no one knew what could create something so narrow and so long. Later observations showed that the jet contained charged particles moving at speeds close to the speed of light. No ordinary star or cluster of stars could produce such a structure. It required a mechanism that involved extreme gravity, strong magnetic fields, and incredible energy output. Once again, the clues pointed to something powerful buried in the galaxy's core. but astronomers still lacked direct evidence of what that object was. In the middle of the 20th century, new instruments allowed researchers to study the central regions of galaxies more closely. Spectroscopic measurements revealed that gas near the centre of M87 moved at astonishing speeds. These weren't gentle rotational motions. These were high-velocity flows accelerated by gravity far stronger than any normal object could produce. If the central region had contained a dense cluster of stars, those stars would have heated up, collided, or blown apart. They wouldn't have remained stable. The only explanation that fit the data was a massive object so compact that its gravitational pull dominated everything nearby. This idea grew stronger over the decades as more galaxies were studied. M87 became one of the best examples because the signatures were so clear and so extreme. It was becoming increasingly likely that a supermassive black hole was responsible, but proving it required techniques far beyond what existed at the time. Years passed, and each generation of astronomers added something new to the investigation. They refined their measurements, they improved their instruments, they developed theories to explain the behavior of matter under extreme gravity. They observed M87 with telescopes that could detect X-rays, ultraviolet light and infrared radiation. Each wavelength revealed something different. X-rays showed that hot gas near the core was energized by enormous forces. Infrared observations showed structural details hidden behind dust. Ultraviolet measurements revealed the presence of energetic processes that could not be produced by ordinary stars. Taken together, these observations formed a compelling argument, though not yet a definitive one. The centre of M87 was not a calm place. It was a region dominated by intense gravitational forces, rapid motion, and enormous energy release. Nothing known could produce such effects except a supermassive black hole. But seeing the black hole's event horizon, the boundary beyond which nothing escapes, remained out of reach. While these clues were being gathered, theorists continued to refine their work. They calculated how light should bend near a black hole. They explored how matter should orbit in the intense gravitational field. They predicted the shape of the shadow cast by a black hole when surrounded by glowing material. Predictions grew more precise as computers advanced. By the 1990s, simulations showed that a black hole surrounded by an accretion flow should produce a bright ring with a dark centre. The ring's shape depended on the mass, spin, and viewing angle of the black hole. If astronomers could observe that ring, they could measure these properties. The idea that we might one day see such a ring seemed ambitious, but the clues kept encouraging the effort. The fast-moving gas, the strong radio emissions, the powerful jet, and the behaviour of light all pointed toward the same explanation. M87 was not an ordinary galaxy. Its core held an object unlike anything directly observed before. The next clue came not from a new observation, but from a new idea. Using multiple radio telescopes spread across the Earth to act as a single massive instrument. This technique, called very long baseline interferometry, had been used before, but never on the scale required to observe a black hole's shadow. Scientists realized that if radio telescopes in different continents could function together with perfect timing, they could produce images with resolution sharp enough to detect structures near the event horizon of a supermassive black hole. The concept opened the door to possibilities that earlier astronomers could only imagine. It meant that the hints collected over the last century, the quick-moving stars, the intense radio source, the enormous jet, the behaviour of gas, could finally be tested directly. The scattered pieces of the puzzle could come together. Even with this new method, the task remained incredibly difficult. The signals were faint, the region to be imaged was tiny, and the data would need to be processed in ways that required careful calibration. But the clues were too compelling to ignore. M87 had become one of the strongest candidates for a black hole that could be imaged directly. The hints left behind by decades of observations all pointed toward the same conclusion. If any black hole could be captured visually, this was the one. As you continue to relax into this story, it might help to appreciate just how gradual scientific understanding can be. There are moments of excitement, of course, but most discoveries build slowly, piece by piece, with long stretches of uncertainty in between. The story of M87's black hole is an example of that slow accumulation of knowledge. Each observation deepened the picture, each improvement in instrumentation revealed a bit more, and each refined theory provided a better framework for interpreting the data. Throughout much of the 20th century, astronomers debated how to interpret the clues. Some argued that the data could be explained by dense clusters of stars rather than a black hole. Others suggested exotic forms of matter, but as the hints accumulated, the alternatives became less and less plausible. A star cluster would not remain stable under such intense gravity. Exotic matter did not fit the observed behaviours. The black hole explanation withstood every new test. More evidence arrived in the form of high-resolution radio images from earlier arrays. These images showed the base of the jet in finer detail. They revealed that the jet originated extremely close to the central region. The size of the launch point matched what would be expected from a supermassive black hole, and the brightness of the radio emission fit models of an accretion flow spiralling inward. All these clues gradually formed a coherent picture. M87 was home to a black hole so massive that it redefined what scientists thought such objects could do. It wasn't simply a gravitational trap. It was a central engine shaping an entire galaxy. With each passing decade, the evidence grew stronger, and while the world didn't yet have a direct visual representation of the event horizon, the case for its existence had become one of the most robust in astronomy. The last piece that scientists still wanted, a direct image, remained out of reach. But that final step was beginning to look possible. If you let your thoughts soften as you imagine this timeline, it becomes clear that breakthroughs often come from long periods of preparation. A century of clues led to the moment when telescopes around the world connected to form something new. The observations that followed would rely on every hint collected over those 100 years. Without those earlier discoveries, scientists wouldn't have known where to look, what to measure, or what signs to expect. As the clues surrounding M87 accumulated and theories grew more precise, the scientific community began to face a question that didn't have an easy answer. If black holes truly shaped galaxies, if they influenced the flow of matter, and if they bent light in ways predicted by general relativity, then could we ever actually see the region near an event horizon? The idea of imaging a black hole had hovered in the background of astronomical research for decades. It wasn't dismissed as impossible, but it lived in that space between what scientists hoped might be achievable someday and what technology seemed capable of supporting. Yet slowly, almost quietly, the conversation began to shift. What once seemed beyond reach started to look like a challenge rather than a dream. And challenges, in the world of astronomy, often turn into projects that take shape over years of planning. The idea that eventually became the Event Horizon Telescope did not start with a single meeting or a single proposal. It began with the realization that no existing telescope, no matter how large, could resolve something as small as the shadow of a black hole at the distance of M87. Even the largest telescopes in the world could only capture faint hints of the structure around the black hole. The resolution simply wasn't enough. The event horizon appeared too small in the sky. This wasn't because the black hole was physically small, it was enormous, but because it was so far away. Distance shrinks even the most massive objects into tiny points of light. To overcome this limitation, astronomers turned to a technique that had been slowly developing over the 20th century. It was called very long baseline interferometry, and it allowed distant radio telescopes to work together, combining their data to simulate a much larger telescope. The key insight was that two telescopes separated by thousands of kilometres could act like a single instrument with a diameter equal to the distance between them. The farther apart the telescopes were, the sharper the resulting image could become. This method had already been used to study distant galaxies, quasars, and other exotic objects. but using it to observe something as small as a black hole's shadow required scaling it up in a way no one had attempted before. As these ideas gained momentum, scientists began discussing what it would take to create a network of telescopes with baselines large enough to resolve regions near the event horizon. The answer eventually pointed toward a simple but ambitious conclusion. The entire Earth would need to function as one coordinated telescope. No single observatory, no single country, and no single continent could provide a baseline long enough. Only by linking telescopes spread across the globe could researchers achieve the resolution needed to see the shadow of a black hole. This realization marked the birth of what would become the Event Horizon Telescope, though the name would come later. In the early discussions, the focus wasn't on branding or formal organizational structure. It was on the science, the pure, steady question of whether such a network was technically possible. Could telescopes separated by oceans and continents be synchronized precisely enough to collect data simultaneously? Could that data be recorded with enough accuracy to capture the complex signals produced near a black hole? Could the observations be processed in a way that produced an image rather than a tangle of noise? These questions required more than answers written in grant proposals or research papers. They required experiments, and that meant bringing together specialists from many fields: radio astronomers, engineers, atmospheric scientists, signal processing experts, theorists, and computer scientists. The effort would need precise timing systems, highly stable atomic clocks, specialized receivers, and instruments capable of recording huge volumes of data. It was clear from the beginning that this would not be the work of a single institution. It would require cooperation on a global scale. One of the first major steps came from scientists who were already using high-frequency radio observations to study black hole environments. They understood that the wavelengths needed to observe regions near the event horizon were much shorter than what most radio telescopes typically used. Shorter wavelengths provide higher resolution, but they're more difficult to work with. They're easily disturbed by atmospheric conditions. They require very stable equipment, and they demand precise synchronization between telescopes. But if scientists could overcome these difficulties, they could capture details that were otherwise impossible to detect. Gradually, sites around the world began upgrading their equipment. Observatories in the United States, Europe, South America, and Antarctica installed receivers capable of collecting data at extremely high frequencies. They added systems that could store this data at immense speeds. They synchronized their clocks using hydrogen masers, which keep time so accurately that they drift only a few nanoseconds over many days. Each improvement moved the global network closer to becoming a single enormous telescope. As you let your thoughts stay soft and unhurried, imagine what this meant on a practical level. Telescopes that had spent decades working on unrelated projects suddenly became part of a coordinated system. Researchers who had been focused on local observations began participating in discussions about global synchronization. Engineers travelled between sites to help install new hardware. Graduate students ran simulations and tests. Meetings stretched into long nights as teams reviewed data, compared ideas, and planned the next steps. Every part of the project required cooperation, aligning observing schedules, sharing techniques, adjusting instruments, and ensuring that all participating telescopes could gather data at the same frequencies and at the same time. The emerging network didn't yet have an official name, but it was becoming clear that this was more than an experiment. It was an international observatory built not from a single site, but from the combined power of telescopes across the world. The phrase Event Horizon Telescope eventually began to circulate. It captured the essence of the project, a telescope designed to observe the region near a black hole's event horizon. It wasn't a poetic description. It was a literal one. The telescope existed to do exactly that. As the infrastructure formed, scientists began selecting targets that could be observed with this method. The two strongest candidates were the black hole at the centre of our galaxy and the black hole in M87. One was closer, smaller, and obscured by dust. The other was farther away, larger and clearer. Each had advantages, each had challenges. But M87, with its massive size and bright emission at radio wavelengths, became the object that held the most promise for producing a clear image. The process of building the Event Horizon Telescope didn't happen in a straight line. Some years brought fast progress, others brought setbacks. Weather conditions interfered with tests, hardware failed, funding wavered, computers struggled to handle the enormous data loads, but every challenge was met with solutions. Teams refined their methods, they upgraded their systems, they shared data across continents, and slowly, the dream of taking a picture of a black hole began to look like something real. One of the most important components of the project was the ability to store the data collected during observations. Each telescope generated astonishing amounts of information, too much to transmit over the internet. Instead, the data had to be recorded on specialized hard drives and physically transported to central processing centers. This meant that technicians in remote locations, including the South Pole, carefully packed up crates of drives filled with recorded observations and prepared them for shipment. In some cases, the drives had to wait months for transport because weather conditions made travel impossible. The data sat in frozen isolation, preserved until the time came to transport it to the processing facilities. The processing itself required enormous computational power. Once the drives arrived at the correlator centers, one in the United States and one in Germany, teams of researchers worked to align the data sets from each telescope. This was a delicate process. The signals recorded by each observatory had to be matched with nanosecond precision. Even the slightest timing error could distort the final image. The Earth's rotation during the observations had to be accounted for. Variations in atmospheric conditions at each site had to be corrected. The position of each telescope relative to the black hole had to be factored into the calculations. All these details mattered because the image would be constructed not by capturing a picture in the usual sense, but by combining signals collected from telescopes separated by thousands of kilometers. The method required breaking down the radio waves into their frequency components, aligning them and reconstructing the brightness distribution of the source. It resembled assembling a mosaic with pieces scattered across the world. But the mosaic was made of data rather than tiles, and the image would only appear after millions of calculations had been completed. As the collaboration grew, so did the realization that observing a black hole would require not just hardware and software, but a coordinated effort involving hundreds of researchers across different fields. Conferences began, including sessions dedicated to the project. Researchers from different backgrounds found themselves working together in ways that crossed disciplinary boundaries. Instrument specialists collaborated with theorists. Observational astronomers worked with computer scientists. Small research teams merged into larger units. Emails, video calls, and shared documents kept the entire network connected. All of these steps contributed to the birth of the Event Horizon Telescope, but perhaps the most defining moment came when the collaboration agreed that the system was ready to attempt its first major observations. Years of preparation, testing, and refining had led to this point. The telescopes were synchronized, the hardware was installed, the system had passed enough preliminary tests to move forward, and the scientists believed that if conditions cooperated, the network could gather the data needed to resolve the region around a black hole. The decision to proceed was made with both excitement and caution. Success wasn't guaranteed. Weather could interfere, equipment could malfunction, timing could drift. Any number of issues might prevent a clear result. But the collaboration moved forward because the only way to achieve the goal was to try. The scientists who had spent years preparing for this moment knew that even partial data would help refine the system, and if everything worked, they would gather information never before captured. As you continue settling deeper into this narrative, it becomes clear that the birth of the Event Horizon Telescope wasn't a sudden event. It was the culmination of steady, persistent work carried out over many years. The idea grew from scattered discussions into a focused project. Researchers contributed their expertise from around the world. Telescopes upgraded their equipment to match the necessary standards. New methods were developed to process the data. The project took shape not because of a single moment of inspiration, but because of the slow accumulation of effort, much like the accumulation of clues that led scientists to suspect a supermassive black hole in M87. The Event Horizon Telescope was ready to observe. The question now shifted from whether it could be built to whether it could succeed in gathering data sharp enough to reveal the shadow of a black hole. When the preparations were finally in place and the network of telescopes had been upgraded, calibrated and connected in new ways, the focus shifted toward the next challenge. It wasn't enough to simply have the instruments ready. The Earth itself had to become part of the tool. The entire planet needed to act as a single, coordinated eye looking toward the same point in the sky. And doing that required timing so precise and cooperation so extensive that nothing quite like it had ever been attempted before on this scale. Yet this was the only way to see something as small as the shadow of a black hole 55 million light-years away. The first step toward turning Earth into a planet-spanning telescope involved understanding exactly what the telescope needed to do. The Event Horizon Telescope would observe at wavelengths that are particularly sensitive to atmospheric conditions. Water vapour, temperature variations, and even slight disturbances in the air could distort or weaken the signals arriving at each telescope. For the technique to work, each observatory would need clear skies, stable atmospheric conditions, and instruments operating at precisely the same frequency. If any telescope in the network encountered conditions that disrupted the signal, whether due to weather, hardware, or timing, the entire dataset could be affected. This requirement meant that scheduling observations wasn't as simple as choosing a date. The collaboration had to monitor weather forecasts, atmospheric models, and sky conditions at each site around the world. Only when many factors aligned could the team move forward. Each telescope site had its own climate. Some were high in the mountains, where thin air offered excellent observing conditions but unpredictable weather. Others were in deserts, where dry air reduced atmospheric interference, but winds and temperature swings posed challenges. One site was at the South Pole, where temperatures dropped far below freezing, and winter nights lasted months. Coordinating these different environments required patience and flexibility. As you listen comfortably, you might imagine the Earth slowly rotating beneath the sky, carrying each telescope across different positions relative to the target. This rotation was actually one of the key elements of the technique. As the planet turns, the distance between each pair of telescopes changes slightly, altering the effective baseline used to image the black hole. This variation, combined with a full network of telescopes, allows astronomers to sample different parts of the black hole structure. It's similar to the way you might walk around an object to see it from different angles, except in this case the changing angles came from Earth's rotation. To take advantage of this natural motion, the telescopes had to begin observing at nearly the same moment. They had to collect data with extraordinary precision. They had to track the black hole as it moved across their respective skies, adjusting their instruments as needed, and they had to store the data in a way that preserved every detail, even when the signals were incredibly faint. This is where the atomic clocks came in. Each telescope had a hydrogen maser, a type of clock that keeps time so steadily that it drifts only a tiny amount over many hours. These clocks ensured that every piece of data recorded during the observations could be synchronized later during processing. Without these clocks, there would be no way to align the signals accurately, and the entire effort would fail. The clocks didn't just keep time, they held the entire system together. As the observation period approached, teams at each site prepared to operate around the clock. Many of the telescopes needed special attention during the observations. Some were located at high altitudes where technicians had to contend with thin air and rapid temperature changes. Others were in remote locations far from major cities, making communication and coordination more challenging. But each site was staffed with people who had trained for years to ensure that the instruments worked flawlessly. They monitored weather patterns, tuned equipment, checked timing signals, and made sure everything was ready. When the observation window finally opened, the telescopes aimed themselves toward M87. Some sites were just beginning their nighttime hours. Others were in the middle of the day, using radio wavelengths that were unaffected by sunlight. Each location followed a schedule that kept the telescopes tracking the black hole for as long as it remained above the horizon. As the Earth turned, a new pair of telescopes would become visible to each other, forming a new baseline. The global network worked together, telescope by telescope, hour by hour, gathering data in a steady, synchronized movement. During this time, the telescopes recorded enormous amounts of information. Instead of sending the data through internet connections, which would not support the necessary speeds, they stored the signals on specialized drives. These drives wrote data so quickly that only a small handful of systems in the world could handle it. As each telescope collected data, its drives filled with information about the radio waves coming from the region around the black hole. The signals were faint, buried under noise, but the timing and synchronization ensured that the patterns could be reconstructed later. While the telescopes observed, teams monitored the systems continuously. They checked the frequency stability. They confirmed the health of the receivers. They ensured that the clocks continued operating as expected. They adjusted for minor variations in weather. They communicated with other sites to coordinate the overall observation. In some places, the work stretched late into the night. In others, it began before sunrise. The collaboration wasn't just global in scope. It was global in time as well, with different teams working in overlapping cycles. As you relax into this narrative, you might imagine what it felt like at the moment when all the telescopes were observing together. This wasn't just a series of machines pointed at the sky. It was a coordinated effort involving hundreds of people across many countries. The process didn't happen instantly. It unfolded over many hours, but there was a sense of shared purpose that connected everyone involved. They knew that if all went well, the data they collected could change our understanding of black holes. They also knew that if something went wrong, a cloud bank forming unexpectedly over one site, a timing issue in a receiver, a hardware malfunction, another year or more of preparation might be needed. The observation period was intense because so much depended on small details. Each telescope has its own characteristics, its own environmental conditions and its own challenges. But the collaboration had spent years preparing for this moment, and each team understood its role. When the observing sessions ended, the drives were carefully removed, labelled and stored for transport. The data would need to be shipped physically to the correlator centres, where computers would combine the signals. This part of the process took time. The drives from locations like the South Pole couldn't leave until the weather allowed flights to resume, which meant the data remained in isolation for months before travelling to the processing centre. Once the drives began arriving at the correlators, the next stage of the project began. This stage required even more patience. The data from each telescope had to be lined up precisely. Tiny timing differences had to be corrected. Atmospheric distortions had to be accounted for. The Earth's rotation had to be factored into the calculations. The processing required not only massive computational power, but teams of experts who understood how to align and interpret the signals. During this time, the world outside the collaboration waited quietly, unaware of how much work was happening in the background. The scientists involved often worked in quiet offices, computing labs, or conference rooms. They reviewed logs from each telescope. They checked for irregularities in the data. They compared different processing methods. They tested various imaging algorithms. It was slow, careful work, but each step brought them closer to seeing what the Earth-sized telescope had captured. As you stay with the story, you may notice that this part of the journey mirrors earlier parts in its patience. The event horizon wasn't revealed in a single moment. The observation wasn't a quick snapshot. Everything had to be assembled slowly, methodically. The Earth had played its role not just as a home for the telescopes, but as a moving part of the instrument. Its rotation created different baselines, Its geography spread the telescopes across the globe, its varied climates introduced challenges and opportunities, and its scientists and engineers transformed it into a tool capable of resolving a structure smaller than the orbit of Mercury, sitting tens of millions of light years away. This transformation didn't happen because of one breakthrough. It happened because countless decisions, small adjustments, and coordinated efforts aligned in just the right way. The Event Horizon Telescope became a planet-sized eye, not through a single innovation, but through a network of people and instruments working in harmony. It demonstrated what can happen when technology and collaboration come together over long periods of time. The result was an instrument unlike any built before. When all the data had been gathered, and the Earth-sized telescope had finished its long session of coordinated observing, the next part of the journey involved something far less visible, but just as important. It was time to examine the signals themselves. The observations were done, but seeing the shadow of the black hole depended entirely on what the data contained. Each telescope in the array had recorded faint traces of radio waves coming from the region around M87's event horizon. These signals had travelled millions of years before being captured on Earth. They carried information about the motion of matter, the bending of light, and the strength of gravity in one of the most extreme environments in the universe. Now they sat quietly inside stacks of hard drives, waiting to be combined into something meaningful. To understand what this meant, it helps to picture the nature of the light the telescopes were trying to capture. This wasn't ordinary light. It wasn't the type that illuminates a room or paints a sunset. It wasn't even visible to the human eye. The light that the Event Horizon Telescope captured travelled through space as radio waves with wavelengths measured in millimeters. These waves came from the hot, swirling material near the event horizon of the black hole. They were produced by electrons spiralling through magnetic fields at tremendous speeds, releasing energy in the form of radiation. This radiation passed near the black hole, bending around its intense gravity, creating patterns of brightness and darkness that held clues about the invisible boundary itself. But gathering this radiation was only the first step. The real work began with making sense of it. The data from each telescope was not a photograph. It was a record of incoming signals over time. These signals were mixed with noise from the atmosphere, technical variations from each telescope's equipment, and natural cosmic background fluctuations. The data did not arrange itself neatly. It had to be carefully aligned and interpreted before it could form anything resembling an image. This process was delicate because the signals were faint and easily distorted. Even a small timing discrepancy between telescopes could blur the final image. That's why the atomic clocks at each site were so important. They provided the exact timestamps needed to align the data precisely. When researchers began processing the observations, they compared the signals from each telescope, searching for matching patterns. When two telescopes observed the same structure at the same moment, the signals exhibited correlations that could be detected during processing. These correlations formed the foundation of the image reconstruction. As you settle into this part of the story, imagine the effort needed to sift through these massive data sets. The correlator computers that handle the data had to consider how each pair of telescopes observed the target. Every pair formed what scientists call a baseline. Each baseline provided a different piece of information about the structure near the black hole. With telescopes scattered across the globe, the number of baselines grew large enough to sample many parts of the image. But even with this coverage, gaps remained. The Earth does not have telescopes everywhere. There are areas over oceans or inaccessible regions where baselines cannot form. To complete the image from these incomplete pieces, scientists had to rely on algorithms designed to reconstruct the missing information as accurately as possible. At this point, the work involved not only astronomers but also experts in imaging, statistics, and computer science. They developed multiple algorithms to produce independent reconstructions, ensuring that no single method could dominate the interpretation. Each algorithm approached the problem differently. Some aimed to find the simplest structure consistent with the data. Others placed constraints on how bright or how smooth the image should be. Some methods filled in missing information by comparing the black hole environment to simulated ones based on physics. The goal wasn't to produce identical images, but to find consistent patterns across different methods. Before scientists applied these algorithms to the real data from M87, they tested them using synthetic data sets. These tests used simulated black hole environments that mimicked what the Event Horizon Telescope might have captured. The tests helped researchers refine the algorithms and understand how they behaved in different scenarios. They allowed teams to identify potential biases and adjust for them. By the time the real data arrived at the correlator centers, the algorithms had been tested extensively, and the researchers had a clear sense of how reliable the methods might be. But even with all this preparation, the moment when the real data was first processed carried a sense of uncertainty. No one knew exactly what the image would look like. The simulations provided expectations. The theories offered guidance. The clues from decades of hints pointed toward a certain structure. But nature doesn't always match expectations. The raw data held the truth, and the processing teams would uncover it only through careful, quiet work. As the correlators began aligning the signals, small pieces of the structure started to appear in the intermediate outputs. They weren't yet images in the way we normally think of them. Instead, they looked like patterns of brightness variation, hints of structure without sharp edges. These intermediate results suggested that the region near the black hole did contain a ring-like formation, but the full picture was still buried amid countless adjustments and calibrations. To ensure that human expectations didn't influence the final result, the collaboration followed strict procedures. Multiple teams worked on the data independently. They didn't share results at first. They used different software packages, algorithms, and assumptions to avoid converging too quickly on a specific image. This separation helped reduce bias. It allowed each team to reach its own conclusions before comparisons were made. Meanwhile, theorists continued to refine their models. They predicted how matter should behave near the event horizon of a black hole with M87's mass and spin. They calculated how light should bend as it moved through the curved space around the black hole. They simulated the likely thickness of the ring, the asymmetry caused by the orbiting gas, and the appearance of the shadow. These predictions guided the imaging teams, but they did not dictate the results. As more of the data was processed, the correlations between telescope pairs became clearer. These correlations revealed the underlying structure of the light distribution near the black hole. The bright ring that theorists predicted began to appear in multiple reconstructions, not as a single ring, but as a consistent pattern emerging from different methods. The dark center, the shadow, also started to form as an area of reduced brightness. It wasn't completely dark. Noise, gaps in coverage, and atmospheric effects added irregularities, but the shape was unmistakable. It resembled the silhouette predicted by general relativity. At this stage, the collaboration began the process of comparing the independent reconstructions. Slowly, cautiously, they examined where the images overlapped. If all teams saw a bright ring, that ring was likely real. If all teams found the shadow in the same location, that shadow was not an artifact. The consistency across methods built confidence in the result. The differences helped refine the interpretations. Teams worked together to resolve discrepancies, examining how each algorithm weighed the data. The algorithms were not the only tools used during this phase. The researchers also built physical intuition by comparing the images to simulated models. The ring's brightness varied depending on the angle of observation and the speed of rotation of the gas. By comparing the observed ring's brightness asymmetry to models, they could estimate the orientation of the black hole and the direction of the rotation. These comparisons helped determine the black hole's spin axis relative to Earth and the galaxy around it. The process required patience. There were no shortcuts. Each step depended on the accuracy of the previous one. As you continue relaxing, you might imagine the slow rhythm of this work. People sitting in quiet labs, reviewing plots and diagrams, conversations drifting across meeting rooms, hours spent calibrating signals, days spent running algorithms, It wasn't the kind of discovery that happened with sudden flashes of insight. It unfolded like a long, steady sequence, each step revealing a little more. Once the teams felt confident in the consistency of their independent results, they began merging their efforts. They produced a final set of images that reflected what the collaboration as a whole agreed represented the most accurate reconstruction. The bright ring was clear. The shadow was distinct. The thickness of the ring matched predictions from relativity. The symmetry matched the expected Doppler boosting from gas orbiting near the event horizon. Every part of the image connected to long-standing theories. But before the collaboration could share the results with the world, they had to confirm that no alternative explanations could account for the image. They compared the data to models without black holes, including dense clusters of stars or objects composed of exotic theoretical matter. None of these alternatives matched the observations. Only a supermassive black hole, surrounded by an accretion flow and governed by general relativity, produced a structure that matched the image. As the analysis moved toward completion, members of the collaboration began to understand the significance of what they were seeing. The ring wasn't perfect. The shadow wasn't a crisp outline, but the overall structure was unmistakable. They were catching light that had skimmed the edge of an event horizon. They were witnessing the shapes formed by gravity so strong that even photons bent into curved paths. They were observing something that had existed in theory for more than a century but had never been directly seen. As this realization took shape, the atmosphere among the teams shifted. There was still caution, still a need for verification, but also a growing sense of accomplishment. Years of work had come together. The Earth-sized telescope had done what it was designed to do. The faint radio waves that had travelled across millions of light-years had left behind a pattern that scientists could interpret. The image was real, and it showed exactly what they had hoped to find. Through all of this, the black hole itself remained unchanged. It didn't react to being observed. It didn't know that its silhouette was being assembled in distant labs. It continued bending light, moving matter, and shaping the galaxy around it as it had for billions of years. But for the first time, humanity had a way to see what its gravity looked like. Not its form, but the effect it had on the world around it. Even now, thinking about the moment when the image first emerged, it's easy to appreciate how much time, effort, and collaboration it represented. But the journey didn't end with the image appearing in a computer display. That moment was only the beginning of understanding what the light had revealed. When all the processing, cross-checking, calibrating, and algorithm testing had been completed, the teams involved in the Event Horizon Telescope collaboration approached a moment that had been building for years. It wasn't loud or dramatic. It didn't arrive with fanfare. Instead, it unfolded quietly inside a handful of rooms where researchers sat in front of computer screens, watching as the results of months of analysis appeared as pixelated structures, curves of brightness, and patterns that hinted at something familiar. The day the image finally emerged wasn't a single instant, but a gradual realization spreading among people who had spent years preparing for this moment. It began with separate groups who had been working independently. Each group had followed strict guidelines to ensure that no one influenced another's work. They used different software packages, different assumptions, and different methods. The purpose wasn't redundancy. It was protection. Protection against human bias, against expectations shaping the data, and against subtle errors slipping through unnoticed. If all the groups produced something similar, despite using different techniques, then the structure would likely be real. When the first group generated an image that resembled a ring with a darker centre, it brought a moment of silence rather than celebration. The researchers stared at the image, cautious and aware of how much was at stake. They checked their inputs again. They verified that the algorithms had run properly. They asked if something else, some artifact of the processing, might have created a false structure. They didn't immediately call it a black hole shadow. They called it a result that needed to be compared. At another location, a second team completed its reconstruction. This group had approached the data differently, using separate assumptions about how to treat missing information and how to smooth the brightness distribution. Their software had been tested in different ways and refined with different data sets. When their image also showed a ring-like formation with a dark core, the room grew quiet in the same way. The researchers knew that coincidences of this sort were rare, but they also knew the importance of caution. They set the image aside and documented their process step by step. A third team finished its independent reconstruction, then a fourth. Each team had worked in isolation, unaware of the details in the other's images. Step by step the patterns emerged. A bright ring, an asymmetric brightness profile caused by the extreme motion of matter, and a consistent circular shadow. The images were not identical, they didn't need to be, but they matched in their essential structure. 4 independent teams had seen the same thing. As you relax into the rhythm of this part of the story, you might imagine how the news moved through the collaboration, not in excited shouts or sweeping announcements, but in small, careful conversations. People met quietly in offices or connected through calls, sharing what their teams had found. They compared the ring structures, the thicknesses, the brightness variations, the positions of the shadow. They reviewed the ways each algorithm handled noise and missing information. When they laid the independent images side by side, the similarities became impossible to ignore. But even then, the researchers didn't hurry. They performed cross-checks. They tested the images against additional synthetic datasets. They ran alternative imaging methods that were not part of the main lineup of algorithms. They checked for instrumental effects that might mimic the features they saw. They repeated calibration steps. They examined the correlations in the data, looking for patterns that might confirm the ring's shape. This wasn't doubt, it was responsibility. The image they were seeing had implications for physics, astronomy, and our understanding of gravity itself. It couldn't be rushed. Only after these methods converged, after the teams verified their consistency, after nights spent refining the results and days spent comparing them, did the collaboration gather to review the images as a group. This gathering wasn't dramatic. It was thoughtful and deliberate. People sat in a room or connected virtually looking at images arranged on screens, the ring, the shadow, the surrounding brightness. The structure was clear. It was no longer a possibility. It was real. Even then, the moment didn't come with a sudden cheer. It came with a shared sense of something settling into place, a collective breath, the knowledge that years of preparation had finally revealed what no one had ever seen. Light bent around, a black hole's event horizon had formed a ring on their screens. The shadow wasn't a theoretical diagram anymore. It existed as a measurable feature in the universe. Yet despite the significance of this moment, many researchers later described it in modest terms. Some said they felt relief. Others said they felt quiet excitement. A few said they felt disbelief that it had finally happened. There were smiles and there was gratitude, but the atmosphere remained grounded. Science often moves slowly, and breakthroughs rarely feel like dramatic revelations. They feel more like the culmination of steady work, each step building on the last until the result becomes undeniable. Over the next several weeks, the collaboration focused on turning these reconstructions into a final image suitable for publication. This meant reviewing the images for consistency, combining the strongest elements from the independent results, and producing a final version that accurately reflected what the data contained. Each detail mattered. The final image needed to be clear enough for the public to understand, accurate enough for scientists to trust, and transparent enough that anyone could examine the methods used to create it. Teams discussed how to present the image's brightness profile. They debated the best way to show the asymmetry caused by the relativistic motion of the gas. They reviewed the thickness of the ring and how to represent the uncertainties. They ensured that the image's scale matched the underlying data. The goal wasn't to produce a perfect picture. It was to present a truthful one. While this work continued, The world outside the collaboration had no idea that something extraordinary had already been seen. The data had been kept private, not out of secrecy, but out of careful adherence to scientific standards. The image needed to be verified, discussed, and finalized before it could be shared. This allowed the team to remain focused and prevented premature interpretations. The researchers didn't speak publicly about the image. They didn't allow rumors to spread. They kept working, quietly refining the details of what they had found. As the final image neared completion, other tasks had to be coordinated. Papers needed to be written. Explanations needed to be prepared. The collaboration began drafting the scientific publications that would accompany the image. These papers would describe the methods, the data, the algorithms, the uncertainties, and the physical interpretation. They needed to be thorough and accessible, allowing readers to trace each step of the process. The writing took time, but it was part of the responsibility the collaboration felt. Revealing the image wasn't just about showing a picture. It was about sharing everything that supported it. At the same time, teams prepared for the public announcement. They worked with science communicators, graphic designers, and press coordinators to determine how best to explain the significance of the image to a wider audience. The collaboration knew that many people had never heard of M87 or the Event Horizon Telescope. They understood that even fewer were familiar with interferometry, radio astronomy, or imaging algorithms. Part of the task was to build a bridge between the technical details and the sense of wonder the image could inspire. As you stay with this story, imagine how the researchers felt during these weeks. They had achieved something remarkable, but their work wasn't finished. They were preparing not only to share a scientific result, but to introduce the world to a piece of the universe that had never been seen directly. They reviewed their explanations carefully, avoided overstating the implications, and emphasized the collective effort involved. Some of them practiced describing the ring and the shadow in simple terms. Others rehearsed presentations, knowing they would speak to journalists and audiences unfamiliar with the complexities of interferometry. They wanted to convey the excitement without compromising accuracy. The final days leading up to the public release were busy. Teams double-checked the final image, editors reviewed the papers, press materials were finalized, the date of the announcement was set. The presentations were organized so that scientists on different continents could speak at the same time, and then, after all the preparation, the moment arrived. On the day of the announcement, the world watched as scientists stood before screens that displayed the now famous image. Some of the researchers had seen it many times during the previous months. Others were seeing it projected publicly for the first time. The image showed a bright ring with a dark centre, the shadow cast by the event horizon of a black hole in M87. The ring matched the predictions of general relativity. The size matched the mass calculated from decades of observations. The asymmetry matched the motion of matter orbiting near the event horizon. When the image appeared on screens around the world, people reacted in many ways. Some were astonished, some were emotional, some were simply curious. For many people, it was the first time they had ever seen anything related to a black hole. Even though the image was blurry compared to everyday photographs, it represented something profound. It was the first direct visual evidence of a black hole's shadow. It confirmed ideas that had been proposed more than a century earlier, and it provided a tangible connection between theory and observation. As the image circulated online, people shared it with friends and family. It appeared in news articles, social media posts, and scientific discussions. The ring of light became instantly recognizable, even among those who had never studied astronomy. It sparked conversations about gravity, space, and the nature of the universe. For many, it served as a reminder of how much humans can achieve when they work together across countries, cultures, and disciplines. Inside the collaboration, the mood was both celebratory and reflective. Researchers acknowledged the years of effort that led to this moment. They recognized the contributions of colleagues who had worked on related theories, simulations, and technologies long before the Event Horizon Telescope existed. They appreciated the global nature of the accomplishment, and they understood that the image was not the end of the story. The day the image appeared was a milestone, but it was also a beginning. The data held more secrets. The image could be refined. The telescope network could be upgraded. Other black holes could be observed. The collaboration knew that their work would continue, slowly unfolding new details and raising new questions. As you settle deeper into this narrative, you might appreciate that the moment the image appeared was not defined by dramatic music or cinematic lighting. It was defined by careful science, patient effort, and the quiet realization that something once considered unseeable had become visible. The bright ring wasn't just a feature of a distant galaxy. It was evidence of gravity behaving exactly as predicted under the most extreme conditions known. When the image of M87's black hole was released to the world, people everywhere referred to it in different ways. Some called it a circle, some called it a shadow, some called it a landmark, a step forward, a symbol of what science can accomplish. But the phrase that lingered most in people's minds was something simple and descriptive: a ring of fire. It was not fire in any literal sense. It wasn't burning or consuming anything the way flames do, but it glowed with the intensity of matter heated to incredible temperatures, pressed and accelerated by the most extreme gravity nature can produce. It was the boundary between visibility and invisibility, between brightness and darkness, between what we can observe and what exists beyond our reach. And in a quiet, steady way, that ring of light changed human history. To understand why the image resonated so deeply, you can imagine the collective anticipation that had been building for more than a century. Scientists had theorized about black holes long before they had evidence for them. They had predicted the existence of event horizons, described mathematically how light would behave near them, and worked out the curvature of space-time around these massive objects. But all of that lived in equations and models. People accepted the idea of black holes because the math was convincing and the indirect evidence was strong, but they were still abstract. They were real in theory, but not yet real in the way that a photograph or a measurement can make something feel tangible. The image of M87 was the moment when all those theories crossed a threshold. The ring of light surrounding the shadow was not a diagram. It wasn't an artist's interpretation or a simulated rendering. It was data from the universe itself, recorded by telescopes across the Earth. The shape and brightness distribution matched exactly what general relativity predicted. The dark centre was the region from which no light could escape. For the first time, people could see, not just imagine, but see, what happens at the edge of a black hole. This was the heart of why the image changed history. It bridged a gap that had existed since the early days of physics. For more than 100 years, the idea of a black hole had relied on trust in equations. Einstein's theory of general relativity had become one of the most successful frameworks in science, but it had never been directly confirmed in the region of strongest gravity. Most tests of relativity occurred in places where gravity was relatively gentle: the orbit of Mercury, the bending of starlight during an eclipse, the timing of pulsars in binary systems. These tests were impressive, but they involved conditions far less extreme than those near a black hole. For relativity to be fully tested, scientists needed to study gravity in its strongest form. The ring of fire around M87's shadow provided that opportunity. Its size, shape, and brightness allowed scientists to compare the observation directly with predictions from general relativity. When they did, the match was extraordinarily close. The diameter of the shadow corresponded almost exactly to what the theory predicted for a black hole with M87's estimated mass. The asymmetry and brightness, the part of the ring that appeared brighter on one side, matched the relativistic effects of matter orbiting at nearly the speed of light. The thickness of the ring told scientists about the distribution of hot gas near the event horizon. Everything aligned. As you let yourself ease further into this story, you might appreciate that the significance of the image wasn't only scientific, it was cultural. It reached people who had never studied astronomy, physics, or cosmology. The image appeared on news broadcasts, on magazine covers, in classrooms, on social media, and in conversations between people who had never before spoken about black holes. It became a universal symbol of discovery. For many, it represented the idea that the universe still contains mysteries, and that humans, through cooperation and curiosity, can reach beyond previous limits. The ring also carried emotional weight. Some people looked at the image and felt a sense of scale, realizing how small Earth is in comparison to the structures in the universe. Others felt a sense of connection, imagining the light that had travelled for millions of years before appearing on a screen. Some saw the image as a reminder of how far science has come, from early telescopes made of glass and metal to a global network working as a single instrument. The moment was not only about physics, it was about human creativity and perseverance. Within the scientific community, the image had additional effects. It provided direct evidence that supermassive black holes exist, not just as inferred objects but as structures with measurable features. It confirmed that accretion flows behave in predictable ways near event horizons. It validated many assumptions built into simulations and allowed theorists to refine their models with new data. The image also opened the door to future measurements. By observing the black hole at different frequencies and at different times, scientists could track changes in the accretion flow, measure magnetic field behavior, and study how matter moves in one of the most extreme environments known. But beyond its scientific and cultural significance, the Ring of Fire changed history in another way, by demonstrating what global collaboration could achieve. The Event Horizon Telescope was not the work of one country or one institution. It involved observatories from many continents, researchers from diverse fields, and teams who worked together across enormous distances. The collaboration showed that scientific discovery at this scale requires cooperation, shared resources, and collective planning. It became an example for other large-scale projects, demonstrating that humanity can reach remarkable achievements when people pool their expertise. The moment the image was released, people around the world celebrated not only the result but the process behind it. They saw the value of building networks that span borders. They saw how different cultures and institutions could work toward a common goal. They saw how young scientists, established researchers, engineers, technicians, and students all played essential roles, and they saw that challenges that once looked impossible could become feasible when approached with patience, collaboration, and long-term dedication. One of the more subtle ways the image changed history was by altering how people imagine black holes. Before the image, most depictions of black holes came from movies, animations, or artistic interpretations. These were often stylized, dramatic, or exaggerated for effect. After the image appeared, people had a reference that was grounded in reality. The Ring of Fire became the standard image of what a black hole looks like when surrounded by glowing matter. It became part of the visual language of science. The image also motivated new questions. Once people saw the ring, they wanted to know more about what was beyond it. They wanted to understand why the shadow appeared as it did, why the brightness varied, and what the structure revealed about the black hole's rotation. The image sparked curiosity in people who might never have explored astrophysics otherwise. Teachers used it as a starting point for lessons. Students wrote papers about it. Artists incorporated it into their work. Writers referenced it in books and articles. It became a symbol not only of scientific achievement, but of the human desire to explore. Within the collaboration, the image inspired new research directions. Scientists began planning observations at higher frequencies, which could reveal finer details near the event horizon. They discussed adding more telescopes to the network to improve the resolution. They considered observing the black hole over long periods to track changes in the ring. The image was a beginning, not an endpoint. As you continue listening, imagine the people who had worked for years on the Event Horizon Telescope sitting together during this period. Some of them had devoted decades to studying black holes. Others had joined more recently. But all of them understood that the image represented a milestone not just for their project, but for the field as a whole. They reflected on the long path that led to this moment, the early hints, the gradual accumulation of evidence, the development of interferometry, the construction of telescopes in remote locations, the years of planning, and the careful analysis of the data. The Ring of Fire wasn't just a product of technology, it was a product of persistence. One of the powerful aspects of the image was that it allowed people to see something that had once been considered unseeable. For decades, black holes were known only through their effects on surrounding stars and gas. The event horizon, the boundary itself, was something no one expected to observe directly. Theoretical papers often stated that black holes could never be imaged, because light from within the event horizon cannot escape. And yet, by imaging the glowing material just outside that boundary, the Event Horizon Telescope managed to capture the silhouette. It was as close as nature allowed humans to get. The shadow was the fingerprint of the event horizon, the mark left behind by something that cannot emit light. Seeing this shadow changed the way many scientists thought about observation. It demonstrated that even when something is invisible, the universe can offer ways to infer its presence through careful study. It showed that boundaries that seem absolute might still leave traces that can be explored, and it encouraged researchers in other fields to consider whether similar strategies could reveal structures once thought impossible to detect. Another way the ring changed their history was by validating the role of computational astronomy. The image existed not only in the sky, but in algorithms, in signal processing, and in software that pieced together data recorded across the planet. The ring demonstrated that modern astronomy is not just about lenses and mirrors, but also about data science, simulations, and advanced imaging methods. It brought visibility to the importance of interdisciplinary skills, showing that coding, mathematics, engineering, and observational astronomy all contribute to major discoveries. Even though the world reacted strongly to the image, the scientists themselves remained grounded. Many expressed humility. Some noted that the image was only the beginning of a longer story. Others pointed out that despite its significance, the image represented just one black hole, and that the universe contains countless others waiting to be studied. The ring didn't answer every question. It opened new ones. But this is what made the moment profound. Progress in science often comes from the questions that arise when answers are finally found. As you let your mind rest gently with these ideas, you might appreciate how the Ring of Fire brought together past, present, and future. It connected a century of theories to a moment of observation. It turned a mathematical prediction into a visual reality. And it paved the way for future studies of black holes, gravity, and the structure of space. The ring didn't change history because it was dramatic or bright. It changed history because it represented understanding, careful, steady, collaborative understanding, made visible through light that had travelled across space for millions of years. It reminded people that the universe still contains mysteries worth pursuing, and that human beings can uncover them through patience, cooperation, and curiosity. When the image of M87's black hole spread across the world, it prompted a wave of excitement and curiosity, but it also opened a deeper doorway into the nature of the universe. That single glowing ring shaped by extreme gravity carried within it answers to questions that scientists had asked for more than a century. It didn't just confirm that black holes exist. It revealed new details about how space behaves near them, how time stretches and slows, and how gravity operates in the most intense conditions humanity has ever observed. In a gentle, steady way, M87 offered an opportunity to understand our universe more clearly. To appreciate what M87 reveals, imagine the environment surrounding its black hole. Space there is not empty in the usual sense. It is filled with gas heated to extraordinary temperatures, magnetic fields twisted and stretched by rotation, and particles moving at speeds close to that of light. All of this unfolds in a region where the pull of gravity is so strong that even time itself behaves differently. While we commonly think of gravity as the force that pulls objects downward or keeps planets in orbit, near a black hole, gravity becomes something more fundamental. It alters the very geometry of space. It changes the rate at which clocks tick. It bends the paths of photons that would normally move in straight lines. The ring of light surrounding M87's shadow is one of the clearest illustrations of gravity, acting not as a simple force but as a curvature of space-time. Light normally travels in straight lines, but when it passes near a massive object, general relativity tells us that the object curves the space around it, causing the path of the light to bend. In everyday situations, this bending is tiny. Light passing near Earth bends barely at all. Light passing near the Sun bends enough to be detected during eclipses, but not enough to disrupt daily experience. For a black hole the size of M87's, however, the bending becomes so extreme that light can actually orbit the black hole before escaping. This orbit is not stable for long, but the momentary looping of photons creates a ring-like structure that outlines the event horizon. This behaviour was predicted decades earlier, but until the Event Horizon Telescope captured the image, it had never been directly observed. M87 confirmed that light behaves near a black hole exactly as relativity describes. This was an important milestone. It showed that Einstein's equations still hold in one of the most extreme environments known. If the shadow had been a different size or shape, it would have raised questions about whether relativity needed to be modified. Instead, the match was remarkably precise. The diameter of the shadow corresponded to what would be expected for a black hole with M87's estimated mass. This agreement strengthened confidence in general relativity at a scale far beyond any previous test. Another aspect revealed by M87's image involves the behaviour of time. Near a black hole, time passes more slowly compared to regions farther away. This effect, known as gravitational time dilation, is a consequence of space-time curvature. The stronger the gravity, the slower time moves. For example, if two observers were to watch an event unfolding near the black hole, one close to the event horizon and one far away, the distant observer would see the event unfold more slowly. This difference is subtle near Earth, noticeable near neutron stars, and extreme near black holes. Although the Event Horizon Telescope cannot directly measure the flow of time, the behaviour of matter and light near the black hole reflects the dynamics predicted by time dilation. The ring's brightness distribution, the speed at which the gas orbits, and the thickness of the ring all depend on how gravity influences the passage of time. To appreciate what this means, imagine gas spiralling toward the event horizon. As the gas gets closer, relativity tells us that its motion becomes more influenced by the curvature of space-time. The gas orbits faster and experiences stronger gravitational effects. From the perspective of a distant observer, the gas appears to slow down as it approaches the horizon, even though locally it continues to move rapidly. This interplay between local motion and distant observation contributes to the brightness pattern we see. The side of the ring where the gas is moving toward Earth appears brighter because the motion increases the energy of the light reaching us. This effect is predicted by relativity and is known as Doppler boosting. The opposite side appears dimmer because the gas moves away from us. The fact that this pattern appears so clearly in the image is further confirmation that relativity accurately describes the motion of matter in these extreme conditions. The image also sheds light on the structure of space-time near the event horizon. The shadow is not a representation of the black hole's surface, because black holes have no surface, but rather the boundary beyond which light cannot escape. The darkness in the centre of the ring represents an absence of light from within that region. It is the silhouette cast by curved space-time itself. The ring around it is formed by the photons that skim the edge of this boundary, held temporarily in orbits before escaping. This delicate balance of light and darkness forms the structure of the image and serves as direct illustration of the event horizon. For many years, scientists wondered whether black holes truly had event horizons, or whether they were instead exotic objects with unusual surfaces that could reflect or emit light in unpredictable ways. The image from M87 provided strong evidence that event horizons do exist as predicted. If the central region had emitted light or reflected light in a way inconsistent with a black hole, the shadow would not appear as it does. Instead, the darkness at the centre matches the characteristics expected from a region where light cannot escape. This finding supports the idea that black holes are genuine spacetime structures, not simply extremely dense objects with unusual material properties. Beyond the behaviour of light and time, M87's black hole offers insights into the role black holes play in shaping galaxies. The energy emitted from the accretion flow and the jet influences the entire galaxy. The jet extends thousands of light years and carries energy that affects gas clouds and star formation. This demonstrates that black holes are not isolated entities, but are connected to the evolution of galaxies. Their gravity doesn't just affect the immediate surroundings, but contributes to the movement and behaviour of matter on large scales. M87's jet is one of the clearest examples of how black holes can regulate the environment around them. Understanding the physics behind the jet helps scientists probe deeper into the behaviour of magnetic fields near the event horizon. The jet is believed to be powered by the rotation of the black hole and the magnetic fields present in the accretion flow. As matter spirals inward, it drags magnetic fields into tight loops. These fields become twisted and amplified. Under the right conditions, the energy stored in the magnetic fields can be released in the form of an outgoing jet. This process, known as the Blandford-Znajek mechanism, had been theorized for decades but lacked direct observational support. The image of M87's black hole, combined with studies of the jet's structure and brightness, offered new evidence that this mechanism may indeed be responsible for the jet's power. This is another way in which M87 reveals the nature of space-time. The rotation of a black hole, known as its spin, influences how magnetic fields behave near the event horizon. The rotation drags space-time with it, an effect predicted by relativity called frame dragging. When space-time itself twists near the black hole, the magnetic fields and charged particles respond. The result is a complex environment where the boundary between space and time moves in ways that affect everything around it. These effects are subtle and difficult to measure, but the presence of the jet and its orientation relative to the accretion flow offer clues about how rapidly the black hole is spinning. As you continue to settle deeper into this narrative, you might reflect on how M87 allowed scientists to see space-time not as an abstract idea, but as a physical entity that shapes the universe. The curvature of space-time determines the paths of stars, the orbits of gas clouds, and the motion of photons near the event horizon. It defines the silhouette of the black hole and creates the ring of light. These are not just theoretical predictions. They are real features captured by an instrument built from telescopes across the Earth. M87 also reveals something important about the scale at which relativity operates. Before this image, relativity had been tested extensively, but mostly in weaker gravitational fields. Observing the strong field near a black hole offers a test of relativity at a scale that had never been accessible before. The success of the theory in predicting the shape and size of the shadow suggests that relativity remains valid even under extreme conditions. This does not mean that relativity is the final word on gravity. Scientists still seek a theory that unifies relativity with quantum mechanics, but it provides strong evidence that the theory remains robust across a wide range of environments. Another way M87 reveals the nature of space and time is through the relationship between information and the event horizon. Theorists have long debated what happens to information that falls into a black hole. Some have suggested that information is lost, challenging the principles of quantum mechanics. Others believe that information is preserved in the structure of the event horizon, or in the radiation that black holes emit. While the Event Horizon Telescope cannot directly resolve this question, the image adds context to the discussion. It shows that the event horizon behaves as predicted, and that the flow of matter near it is consistent with theoretical models. These observations help refine the question scientists ask about the nature of information in extreme gravitational fields. The image also reveals something about the scale of the universe itself. The fact that humans could capture light that travelled across millions of light years to skim the edge of a black hole speaks to the interconnectedness of cosmic structures. The ring of light we see today originated long before Earth existed in its current form. When the photons left the region near the event horizon, the continents had different shapes, ecosystems were different, and the sky above Earth would have looked unfamiliar. The light carried information across cosmic time, arriving just as humanity had developed the technology to record it. This timing was not intentional, but it highlights how observations allow us to reach across vast distances and access moments from the deep past. As you remain comfortable and let your thoughts move at an easy pace, you might consider that the image of M87 is also a reminder that the universe is governed by rules that can be studied, understood, and applied. Space is not random. Time is not chaotic. Gravity is not a mysterious force acting without pattern. These elements work together in structured ways, and observing M87 allows us to see that structure in action. The ring of fire is not just a beautiful pattern. It is the visible imprint of the laws of physics. The image also reveals something about the scale of human understanding. Just as the universe is vast, the effort needed to uncover its secrets requires depth, patience, and collaboration. M87 shows that progress in science comes from building on the work of many generations. It comes from refining instruments, developing theories, testing ideas, and bringing people together. The image was not created by one person, one instrument, or one country. It was created by a network supported by thousands of contributions. This model reflects how science advances through cooperation. The more scientists analyse M87, the more subtle insights emerge. Studies of polarisation, the direction in which light waves vibrate, have provided information about the magnetic fields near the event horizon. Observations at multiple frequencies allow scientists to map different layers of the accretion flow. Continued monitoring may reveal fluctuations in brightness that trace the motion of hot spots moving around the ring. Each of these findings helps refine our understanding of space-time near the black hole. Yet the story does not end with what we have learned so far. M87 continues to reveal new aspects of space, time, and gravity as the Event Horizon Telescope observes it across different years. The ring may shift slightly over time as the accretion flow moves. The jet may change its brightness or shape. These variations remind us that black holes are not static objects. They are dynamic environments, constantly shaped by the matter and energy flowing around them. As we drift onward from the ring of light surrounding the event horizon, the story of M87 expands far beyond the boundaries of the black hole itself. The environment around it is full of motion and structure, and nowhere is this more visible than the enormous jet that extends outward from the galaxy's centre. This jet is one of the most remarkable features in the universe. It stretches across space like a cosmic lighthouse beam, carrying energy and matter over distances so large that the human mind can only approach them through patient, steady imagination. To look at it closely is to understand that black holes are not silent, isolated objects. They are engines capable of shaping their galaxies in ways that are both dramatic and long-lasting. To begin appreciating this jet, imagine the region very close to the black hole. Here, gas spirals inward, heated to extreme temperatures by friction, magnetic fields, and gravitational compression. The gas doesn't fall straight into the event horizon. It circles around the black hole in tight orbits, forming a flow that generates enormous amounts of radiation. But not all of that gas ends up crossing the event horizon. Some of it becomes part of a process that launches the jet outward. This process is not simple, and it has taken decades of study to understand even in broad terms. But the basic idea is that the magnetic fields near the black hole play a central role. As matter orbits and drags these magnetic fields along with it, the fields become twisted and amplified. They store energy in the form of tension, much like a stretched elastic band. Under the right conditions, this stored energy can be released in the form of an outflow of particles. The black hole's rotation contributes to this process by dragging spacetime itself, which helps accelerate particles along magnetic field lines. The result is a narrow, focused beam of matter and energy that shoots outward away from the black hole at astonishing speeds. In M87, this jet is particularly large. It is so powerful that it can be observed across many wavelengths, from radio waves to visible light to X-rays. Astronomers have been studying the jet for more than a century, long before the Event Horizon telescope captured the image of the black hole. Early photographs taken in the 1910s showed a faint streak of light extending from the galaxy's core. Over the decades that followed, telescopes improved, and the structure of the jet became clearer. It became evident that the jet was composed of charged particles, moving at speeds close to the speed of light, guided and confined by magnetic fields. The scale of the jet is almost difficult to comprehend. It stretches tens of thousands of light years from the galaxy's centre. If you imagine travelling along it at the speed of light, it would still take many thousands of years to reach the point where the jet fades into the surrounding intergalactic medium. And yet, from Earth, the jet appears as a delicate line, a thin structure visible in long exposure images. This contrast between physical size and visual subtlety is one of the striking features of astronomy. Enormous structures can appear fragile, while tiny structures can appear dominating when viewed up close. As you continue relaxing into this story, imagine following the jet from its origin near the black hole outward into space. At its base, the jet is narrow, compact, and incredibly bright in radio wavelengths. It is so bright that the region near the launch point has been one of the most studied locations in all of radio astronomy. As the jet moves outward, it begins to widen slightly, though it remains focused enough to stay collimated across vast distances. This focus is maintained by magnetic fields that wrap around the jet, preventing it from dispersing too quickly. Without these magnetic fields, the jet would lose its structure early on and spread outward in a diffuse cloud. The jet doesn't remain uniform as it travels. It contains knots or bright spots caused by variations in density and magnetic field strength. These knots can move along the jet over time, providing clues about the speed of the particles and the energy driving them. Observations have shown that some of these knots move at apparent speeds faster than light. This is not a violation of physics. It is an optical effect caused by the combination of high speeds and the angle at which we observe the jet. The apparent superluminal motion is one of the signatures that the particles in the jet are travelling extremely fast, close enough to the speed of light that relativistic effects become important. One of the remarkable aspects of M87's jet is how it remains coherent across such long distances. As it travels, it interacts with surrounding gas and dust, but it maintains its shape. This interaction produces shocks, heating the surrounding material and creating regions of emission that astronomers can observe. These interactions reveal information about the density and structure of the intergalactic medium, providing insights into the environment surrounding the galaxy. For researchers studying galaxy evolution, such details are invaluable. They show how energy from the black hole can influence regions far beyond the central core. The jet doesn't just illuminate the surroundings, it also carries away energy and angular momentum from the black hole and the accretion flow. This means that the jet is part of a feedback system. The energy released through the jet affects the behaviour of gas in the galaxy, influencing how stars form and how matter moves. In some galaxies, jets can heat surrounding gas so much that it can no longer cool effectively. When gas cannot cool, it cannot condense to form new stars. In this way, black holes can regulate star formation on galactic scales. Studying the jet in M87 has revealed how powerful this feedback can be. The jet's energy affects clusters of gas both inside and outside the galaxy. Observations in X-ray wavelengths show bubbles and cavities in the hot gas surrounding M87. These structures are the result of the jet pushing against the gas, displacing it and transferring energy into it. Such interactions help astronomers understand how galaxies maintain their shapes and how they avoid becoming too dense at their centres. Without this feedback, galaxies might collapse inward or experience uncontrolled bursts of star formation. As scientists studied the jet more closely, they noticed that it holds clues about the black hole's rotation. The direction of the jet aligns with the black hole's spin axis. This alignment occurs because the rotation of the black hole influences the orientation of the magnetic fields that launch the jet. By measuring the direction and stability of the jet, astronomers can infer details about the black hole's spin. This is important because spin affects many aspects of a black hole's environment, including how much energy can be extracted through magnetic fields and how stable the accretion flow remains. Even though the jet has been observed for over a century, recent images and studies have provided deeper insight into its structure. High-resolution radio images show the jet's base in remarkable detail, revealing the shape of the flow and the behaviour of the magnetic fields near the launch point. These images show that the jet begins very close to the event horizon, consistent with theoretical predictions. This connection between observation and theory helps confirm that the processes driving the jet are consistent with the mechanisms predicted by general relativity and magnetohydrodynamics. The jet also helps scientists understand how energy is distributed in the universe. Much of the radiation we see from distant galaxies comes from jets powered by supermassive black holes. These jets carry energy far from their sources, affecting the environments of neighbouring galaxies and clusters. The energy carried by the jet in M87 is immense. Even though it represents only a small fraction of the black hole's total available energy, it is enough to shape structures on scales far larger than the galaxy itself. As you continue listening, imagine what it means that such a narrow beam of particles can travel so far. The jet moves through space for thousands of light years without losing its structure. It maintains its direction, guided by magnetic fields and the rotation of the black hole. It interacts with clouds, shock fronts, and intergalactic gas, leaving visible signatures of its passage. This persistence is one of the reasons jets are such powerful tools for studying the universe. They connect the smallest scales, near the event horizon, with the larger scales, across clusters of galaxies. The jet also reveals how stable black hole systems can be over long timescales. Observations show that the jet in M87 has existed for millions of years. This means the black hole has been accreting matter and producing energy consistently over that time. It reflects a balance between inflow and outflow, between the gravitational pull of the black hole and the magnetic forces driving the jet. This balance tells astronomers that the black hole is not simply consuming matter in bursts, but is instead part of a long-term cycle of energy production. Another fascinating aspect of M87's jet is its polarization. Light emitted from the jet is polarized, meaning the electric and magnetic fields of the light waves have a preferred orientation. This provides information about the magnetic fields within the jet. Observations of polarization patterns help scientists map the structure of these fields and understand how they guide the particles. Polarization studies have shown that the magnetic fields in M87's jet are well ordered, supporting the idea that they play a central role in launching and maintaining the jet. In more recent years, the Event Horizon Telescope has added polarization imaging to its capabilities. This allows researchers to see not only the brightness of the region around the black hole, but also the orientation of the magnetic fields. These studies reveal how the magnetic fields behave near the event horizon, providing insight into the processes that launch the jet. They show that the fields are strong and structured, and that they thread through the accretion flow in ways that match theoretical models. As you stay with this story, it becomes clear that the jet is not a secondary feature. It is a central part of how M87's black hole interacts with its galaxy. The jet reveals the black hole's rotation, the strength of the magnetic fields, the structure of the accretion flow, and the distribution of energy across the galaxy. It helps explain why certain regions of the galaxy behave as they do, and why star formation occurs in some areas but not in others. It connects the small scale of the event horizon to the large scale of the galaxy itself. The jet also illustrates the interconnectedness of cosmic structures. It begins in one of the smallest regions, the environment near the event horizon, and extends into some of the largest, the intergalactic medium. Along its path, it shapes the gas around it, affects the temperature of its environment, and influences the formation of stars. It is a bridge between scales, a demonstration of how local processes can have global effects in the universe. And yet, despite all we have learned, the jet still holds mysteries. Scientists continue to study how the particles are accelerated to such high speeds, how the magnetic fields remain stable over long distances, and how the jet maintains its structure across thousands of light years. New observations at different wavelengths combined with improved theoretical models are helping refine our understanding. Each observation reveals a new detail, and each detail brings us closer to understanding the full picture. The jet gently guides us toward deeper questions. Understanding it helps us understand the environment near the event horizon, the behaviour of matter under extreme gravity, and the role of black holes in the evolution of galaxies. It shows us how dynamic and interconnected the universe truly is. The story of M87 and everything we have learned from it, we eventually reach a point where the questions grow more complicated than the answers. The jet, the ring of light, the shadow, the accretion flow, the bending of space and the slowing of time. Each of these pieces fits into a framework that scientists understand reasonably well. But surrounding every piece is a larger world of physics still waiting to be explained. It's one of the interesting things about black holes. The closer we get to understanding them, the more their mysteries expand outward. M87 has shown us extraordinary details, but it has also revealed gaps in our knowledge, subtle inconsistencies, and deeper layers that haven't yet been resolved. This is not a failure, it's part of how science progresses. Every major discovery opens the door to new questions, and when we look at M87 closely, we begin to see not just what we understand about black holes, but also what remains unclear. This section of the story is quieter and more reflective, because it involves edges of our theories, edges of our models, edges of what our instruments can currently reveal. To begin grounding this exploration, imagine taking a step back from the specific observations we've discussed so far. The image of the shadow, the structure of the jet, the behaviour of magnetic fields. These all fit into our understanding of gravity as described by general relativity. Einstein's framework has succeeded in predicting countless phenomena over more than a century. It has passed every observational test. But even though relativity is extraordinarily successful, it is not complete. It doesn't fully describe the physics that occur in the most extreme conditions, and black holes are among the most extreme objects in the universe. One of the biggest open questions concerns the nature of the singularity at the centre of a black hole. According to classical relativity, inside the event horizon, space-time collapses to an infinitely small point with infinite density. This singularity is not something we can observe directly. It is hidden behind the event horizon, and even the most advanced instruments cannot access it. But the math suggests that these singularities exist. Yet physicists also know that infinities typically signal a breakdown in a theory, not a real physical property. This is one of the first areas where M87 pushes us toward physics we don't yet understand. The event horizon hides the singularity, but the behaviour of space-time near the horizon still depends on the conditions inside. If relativity predicts an impossible infinite density, then something must happen before that limit is reached, something beyond our current theories. That something is often referred to as quantum gravity, the yet unwritten theory that merges relativity, which governs the very large, with quantum mechanics, which governs the very small. Black holes are natural testing grounds for this missing theory. The environment near the event horizon involves intense curvature of space-time, strong gravitational fields, and high-energy particle interactions. Yet quantum mechanics also applies at small scales, even near black holes. M87 helps reveal the structure of space-time near the event horizon, but it doesn't answer the question of what happens inside. This boundary between known and unknown physics is one of the deepest mysteries of the universe. Another area of uncertainty involves the information paradox, a famous puzzle that has challenged physicists for decades. The paradox arises from the idea that information about matter that falls into a black hole might be lost forever. In classical relativity, nothing that crosses the event horizon can escape, and no information about the interior can influence the exterior. But quantum mechanics states that information cannot be destroyed. The tension between these principles forces scientists to confront a conflict between the two most successful theories in physics. While M87's image doesn't resolve the paradox, it adds context. It shows that the event horizon behaves as expected in relativity. The shadow is consistent with a region from which no light escapes. The accretion flow matches theoretical predictions. But this still leaves the underlying question: what happens to information that falls in? Does it remain encoded in some structure at the event horizon? Is the event horizon itself more complicated than relativity suggests? Does information leak out subtly through processes we haven't discovered? Or does a full theory of quantum gravity provide an entirely new perspective that makes the paradox disappear? These questions sit right at the boundary of what M87 reveals. The image shows that the horizon behaves as relativity predicts, but it cannot tell us whether relativity holds true all the way inward. It leaves room for deeper theories to emerge. Another mystery involves the exact mechanisms that launch and sustain the jet. Scientists have models describing how magnetic fields and rotation can extract energy from a black hole, but the details are still unclear. The magnetic fields near the event horizon are stronger and more organized than expected, and the polarization patterns captured by the Event Horizon Telescope offer clues, but not definitive answers. One of the open questions involves how the jet remains stable over such vast distances. Magnetic fields guide the jet, but the fields themselves must remain coherent across thousands of light years. The mechanism that preserves this structure is not fully understood. Even the acceleration of particles within the jet is a puzzle. The particles move at nearly the speed of light, but the exact processes responsible for accelerating them remain under investigation. Shock waves, magnetic reconnection, and turbulence all play roles, but the specifics depend on conditions that are difficult to model from Earth. The jet's brightness varies over time, suggesting changes in energy or density, but these variations do not always match predictions perfectly. As you continue settling into this narrative, you might find it helpful to imagine scientists examining all these details slowly, carefully, step by step. They compare observations to simulations, they adjust variables, they refine the physics. Yet even as the models improve, new uncertainties appear. This isn't a flaw in the process, it is exactly how science expands. Each discovery widens the horizon, revealing new questions beyond it. Another area of uncertainty concerns the role of turbulence in the accretion flow. The gas swirling around the black hole is not smooth or uniform. It is turbulent, chaotic, and constantly shifting. Magnetic fields twist and reconnect. Density varies from place to place. The flow moves between states of order and disorder. These conditions make it difficult to predict the detailed structure of the accretion disk or the exact motion of material. Yet the flow's behavior influences the brightness of the ring, the thickness of the emission, and the shape of the jet. 87's image provided the first detailed look at this region, but it did not answer every question. Scientists still investigate how turbulence behaves near the event horizon, how it affects the motion of particles, and how it influences the variability of the emission. The brightness of the ring changes over time, suggesting that the accretion flow is dynamic. But tracking these changes requires multiple observations across many years. Another uncertainty involves the black hole's spin. Scientists can estimate the spin based on the orientation and stability of the jet, but the exact rate remains difficult to determine. Spin influences the structure of spacetime near the event horizon, including the boundary between stable and unstable orbits. It affects how matter falls inward and how energy is extracted, yet measuring spin directly remains challenging. The Event Horizon Telescope provides clues, but additional observations at different wavelengths and more detailed models are needed to obtain a clearer value. One of the more subtle mysteries involves the thickness of the ring. Simulations based on different physical assumptions produce rings of slightly different thicknesses. Some models predict thinner rings if the magnetic fields are weak, others predict thicker rings if the fields are strong, but the observed ring has a thickness that sits between several theoretical expectations. This suggests that the physics in the region is more complex than any single model captures. It hints at the interplay between turbulence, magnetic fields, and relativistic motion in ways that simulations are still learning to replicate. Another question involves the structure of the photon ring, the layer of light formed by photons that orbit the black hole multiple times before escaping. This ring is expected to be extremely narrow and bright, but in the actual image it blends with a broader ring of emission from the accretion flow. The photon ring is difficult to isolate, and its brightness depends on conditions that are not yet fully understood. Future observations at higher resolution may reveal more details about this structure, helping scientists test relativity even more precisely. M87 also points toward deeper, more conceptual mysteries. One of these involves the nature of spacetime itself. Relativity treats spacetime as smooth and continuous, but quantum theories suggest that spacetime may be granular or fluctuating at extremely small scales. If spacetime does have structure at tiny scales, black holes would be natural places to detect it. Yet current observations cannot resolve such fine details. The event horizon appears smooth because our instruments cannot yet see anything smaller than the wavelength of the radio waves we use. As instruments improve, scientists hope to observe the black hole at higher frequencies, which provide sharper resolution. These observations may reveal finer structures in the ring or new features near the event horizon. If the shadow deviates even slightly from the predictions of relativity, it could indicate new physics. But until those observations become possible, the question remains open. Another conceptual mystery involves the behavior of quantum fields near the event horizon. Quantum field theory predicts that particle-antiparticle pairs constantly form and annihilate throughout space. Near the event horizon, this behavior becomes more complex. Some theories suggest that one particle can fall into the black hole while the other escapes, producing what is known as Hawking radiation. This radiation would cause black holes to evaporate extremely slowly over vast spans of time. But Hawking radiation has never been observed directly, and the rate of evaporation for a supermassive black hole like M87's would be so slow that it is effectively undetectable with current instruments. Still, the existence of the event horizon raises questions about how quantum fields behave in curved space-time. These questions sit at the intersection of relativity and quantum mechanics, but the answers remain incomplete. M87 provides a real environment where these questions can be studied indirectly, but a full understanding requires new theories, new observations, or both. Another mystery lies in the relationship between black holes and dark matter. Dark matter is believed to make up most of the mass in galaxies, yet it has never been directly detected. Some scientists wonder whether dark matter influences the region around M87's black hole, or contributes to the behavior of the jet. Current observations don't provide clear evidence either way, but the possibility remains open, especially as new instruments come online. Even the brightness patterns in the ring raise questions about the behavior of plasma under conditions that cannot be replicated on Earth. Plasma near the event horizon moves in relativistic orbits, interacts with strong magnetic fields, and experiences gravity far beyond anything we experience in ordinary life. Understanding these interactions requires numerical simulations that push the limits of computational power. The simulations are improving rapidly, but they still rely on approximations. M87 challenges scientists to refine their models and develop new ones. As you let your thoughts move gently through these ideas, you might sense that the story of M87 is not only about what we have learned, but also about the boundaries where our knowledge begins to thin. It is about standing at the edge of understanding and looking beyond, not with frustration, but with curiosity. Black holes represent one of the few places in the universe where the known and unknown meet in such a dramatic way. The mysteries surrounding M87 are not obstacles, they are invitations. Each unanswered question is a sign that there is more to discover, more to observe, more to understand. The ring of fire revealed by the Event Horizon Telescope is not a conclusion, it is a doorway. When the first image of M87's black hole appeared, it didn't simply add another piece to the scientific landscape, it shifted the landscape itself. For decades, black holes had been treated as theoretical certainties supported by strong evidence, but always kept at a distance by the limitations of our instruments. We inferred their presence through the motion of stars, through the behaviour of gas, through gravitational waves, and through mathematical predictions that grew stronger with each refinement. Yet despite all of that, there was still a subtle sense that black holes lived partly in an abstract world, a world of equations, diagrams, and conceptual models. M87 changed that. It took something once considered unreachable and brought it into the realm of direct observation. When we say the image reshaped our understanding of the universe, it's not because it created an entirely new theory or overturned existing ideas. Instead, it clarified them. It confirmed their strength. It grounded them in reality. It gave the global scientific community a visual reference point for one of the most extreme objects in existence. And it created a foundation on which the next stages of gravitational research could be built. To understand how significant this shift was, imagine spending your life studying a landscape only through maps. You learn the contours, the elevations, the shapes of the valleys and mountains. You develop an understanding of what the world probably looks like based on consistent, well-tested information. Then, one day, you arrive at an overlook and finally see the landscape with your own eyes. Nothing in your understanding was wrong, but the experience changes you anyway. It adds a dimension that cannot be captured by inference alone. This is what M87 did for black holes. The first way it reshaped our understanding was by validating general relativity in a regime that had never been directly observed. Before M87, Einstein's theory had been tested in strong gravitational fields only in limited ways. The timing of pulsars, the bending of light-near stars, the orbit of Mercury, and observations related to gravitational waves. All of these were impressive, but none involved the extreme curvature of space-time near a supermassive black hole's event horizon. The shadow of M87 provided the first direct look at how light behaves when subjected to the full intensity of gravitational effects predicted by relativity. The size of the shadow matched theoretical predictions so closely that it reinforced the idea that space-time behaves exactly as described, even under the most severe conditions. This wasn't trivial. Many alternative theories of gravity propose deviations from relativity in strong fields. If M87's shadow had been slightly larger or smaller, it could have suggested new physics. Instead, the match was precise enough to eliminate many alternatives and push future research toward refining relativity rather than replacing it. This stability in the theoretical landscape helps scientists focus on the remaining gaps, particularly the intersection of relativity and quantum physics. Another way the image reshaped understanding was by demonstrating the power of coordinated global observation. The idea of turning Earth into a single telescope had been discussed for decades, but M87 proved it could be done successfully. It showed that global interferometry could overcome atmospheric disturbances technical limitations and geographic challenges. The Event Horizon Telescope became a model for how large-scale scientific collaborations might work in the future. Instead of building a single giant instrument, scientists learned how to connect smaller ones across the world. This approach doesn't only benefit black hole research, it has implications for studying distant galaxies, star formation regions, and cosmic magnetic fields. The techniques developed for M87, precise timing, synchronized data collection, massive data processing, have already begun influencing future instruments. The concept of global astronomy became more practical, and new projects are now being designed with worldwide coordination in mind. The image also reshaped how people think about scale. For many, black holes existed in that mental space where numbers become difficult to visualize. Masses measured in billions of solar masses, distances measured in tens of millions of light years, sizes measured in astronomical units. These magnitudes drift into abstraction. M87 gave these abstractions a visual anchor. When people saw the ring, they weren't simply seeing an image. They were seeing a structure larger than our entire solar system. The ring's diameter was enough to stretch across orbit after orbit, yet it appeared to us as a glowing, delicate loop. That contrast between unimaginable size and visual simplicity helped make cosmic scales more approachable. Scientists also gained a clearer sense of how black holes influence the galaxies around them. Before M87's image, the role of black holes in galaxy evolution had been studied primarily through indirect evidence. The connection between black holes and their host galaxies, particularly the correlation between black hole mass and stellar velocity, suggested deep relationships, but the mechanisms behind these relationships remained partly speculative. M87's jet provided a living example of energy being transferred from the black hole to the surrounding medium. Observing how tightly the jet is connected to the region near the event horizon allowed researchers to explore how energy extraction might work. This helped refine models of galactic evolution and gave weight to the idea that black holes do not merely sit at the centres of galaxies, they actively shape them. The polarization studies that followed the initial image reshaped understanding even further. They revealed the structure of the magnetic fields near the event horizon, showing that the fields were strong, ordered, and capable of guiding particles into the jet. This offered a rare confirmation. The mechanisms theorists had proposed for decades were actually visible in the data. Theories about how black holes convert rotational energy into jet power gained new credibility, and researchers gained a clearer picture of the transition zone where matter spirals inward, magnetic fields tighten, and jet launching processes begin. All of this influenced how scientists approach the future of black hole research. M87 made clear that our instruments were capable of probing regions once thought unreachable. It showed that we can image the behaviour of plasmas under gravitational forces so strong they defy ordinary intuition. It also encouraged scientists to refine their questions. Instead of asking whether black holes have event horizons, they can now ask how precisely the horizon behaves. Instead of wondering whether jets originate close to the event horizon, they can now investigate exactly how close. Instead of debating whether general relativity breaks down in strong gravity, they can now study how accurate it remains right up to the boundary of detectability. The image also influenced how simulations are built. Before M87, simulations of black hole environments were compared mostly to theoretical expectations. After the image, these simulations could be compared to actual observations. Differences between the simulations and the observed ring helped scientists refine their models. They adjusted assumptions about magnetic field strength, plasma temperature, and accretion flow dynamics. This refinement improved not only black hole simulations, but also computational astrophysics more broadly. Techniques developed in this process are already being applied to neutron stars, magnetars, and other extreme environments. Another way M87 reshaped understanding involved the philosophy of science itself. It reminded the scientific community that some discoveries take decades of preparation. The The Event Horizon Telescope was not built overnight. It grew from early experiments in interferometry, from improvements in telescope technology, from advances in data storage, and from models built by theorists long before. The project spanned continents, languages, institutions, and generations. M87 showed that major breakthroughs are often the result of long-term commitment rather than sudden inspiration. This understanding helps guide planning for future projects which may require similar levels of global collaboration. At a cultural level, the image shifted how people talk about the universe. It became a point of accessible wonder. Black holes transformed from purely theoretical constructs to objects that people could see. The ring appeared on posters, book covers, and science materials around the world. It made black holes feel less like distant mysteries and more like real parts of the universe that we can study with the right tools. This accessibility encouraged new interest in astrophysics, especially among students and young researchers who saw the image and imagined being part of the next discovery. The image also opened new directions for philosophical and scientific reflection about the nature of knowledge. It reminded us that some objects remain invisible, not because they're too small or too faint, but because their very nature prevents light from escaping. Yet through indirect observation and careful inference, we can still learn about them. This idea has implications for many areas of science, areas where direct observation is impossible, but indirect methods can reveal hidden truths. As you remain settled into this narrative, you might appreciate that M87 reshaped understanding not with shock, but with quiet certainty. It didn't overturn established theories, it strengthened them. It didn't create an entirely new branch of physics, it refined the one we have. It didn't resolve every mystery, it clarified which ones still matter most. The image became a steady reference point, a visual confirmation that the universe behaves according to principles we can study, measure, and understand. Even now, years after its release, M87 continues to influence research. Every time new data is collected, scientists compare it to the original image. They look for changes in brightness, structure, or magnetic field orientation. They use the black hole as a laboratory for physics that cannot be replicated anywhere else. And each new observation shifts understanding a little more. The first image of a black hole was not an endpoint. It was the opening of a new era. For the very first time, humanity didn't just infer the existence of these extreme structures. We saw their influence on light. We saw their shape. We saw the behavior of matter in their grip. Now that this window is open, the next step is to make it wider, clearer, and deeper. The future of black hole observation is one of the most exciting frontiers in astrophysics, not because we expect a single dramatic discovery, but because we are entering a phase where each new improvement reveals layers of detail that were previously invisible. To understand where black hole observation is heading, imagine standing at the edge of a large, dimly lit room. The first image of M87 was like turning on a small lamp in the corner. It illuminated far more than what we'd seen before, but most of the room remains in shadow. The goal now is not simply to light the entire room at once, but to increase the brightness step by step, building instruments that can reveal faint structures, track their evolution over time, and test the limits of our theories with more precision than ever. One of the first steps in this direction is improving the Event Horizon Telescope itself. The original image was made using a network of telescopes spread across the globe, but that network had gaps. These gaps resulted in incomplete sampling of the structures around the black hole. Imaging algorithms filled in some of the missing information, but the results were limited by the number and position of the telescopes. The more telescopes added to the network, the more complete the sampling becomes. Adding new observatories, especially in regions that currently lack coverage, can dramatically improve the resolution and clarity of future images. Several new sites are being considered for inclusion in upcoming observing campaigns. Locations in Africa, the Middle East, and Australia would help fill the geographic gaps in the network. These new stations would allow the Event Horizon Telescope to capture more detailed information about the structure of the ring, the thickness of the photon orbit, and the shape of the accretion flow. Each new telescope acts like a lens added to a camera. It sharpens the overall picture. By increasing the number of telescopes, scientists also improve the ability to track changes over time. Black holes are not static. The accretion flow near M87 brightens and fades, the jet fluctuates, and the orientation of magnetic fields shifts. Capturing these changes requires repeated observations. As the Event Horizon Telescope grows, it will be able to observe black holes more frequently and with greater detail, revealing the dynamics of their environments on timescales of days, months, or years. Another major development in the future of black hole observation involves increasing the observing frequency. The initial image of M87 was taken at a wavelength of 1.3 millimeters. Observing at shorter wavelengths, such as 0.87 millimeters, will provide sharper resolution. This is because shorter wavelengths are less affected by scattering and atmospheric distortions. Higher frequencies allow the network to probe regions even closer to the event horizon, where the curvature of space-time becomes more pronounced, and the light we see has travelled through more extreme gravitational gradients. Observing at higher frequencies is technically challenging. The atmosphere is less transparent at these wavelengths, requiring exceptionally dry and stable air. Telescopes must be equipped with more sensitive receivers, and the data must be processed even more precisely. Yet several telescopes in the network are already being upgraded to support these shorter wavelengths, and future observing campaigns are expected to include them. One of the most significant advancements on the horizon is the plan to place telescopes in space. The idea is often referred to as space-based VLBI, very long baseline interferometry extended beyond Earth's surface. By placing radio telescopes in orbit, scientists can increase the effective size of the telescope array far beyond Earth's diameter. This would result in dramatically improved resolution. Instead of a telescope the size of Earth, we would create one the size of Earth plus the satellite's orbit. The improvement would be comparable to replacing a small backyard telescope with a massive observatory. Using space-based telescopes would allow scientists to image not only the main ring around M87's shadow, but also the photon ring itself. This extremely thin structure forms from photons that orbit the black hole multiple times before escaping. In the current image of M87, the photon ring is blended with the broader emission from the accretion flow, but with higher resolution, one made possible by adding space-based instruments, the photon ring could become visible as a distinct feature. This would provide an entirely new way to test relativity, because the photon ring's shape and brightness depend directly on the curvature of space-time near the event horizon. Several proposed missions aim to make this possible. These missions vary in scale, cost, and scope, but they share the same goal: expanding the Event Horizon Telescope into orbit. Some proposals involve small satellites equipped with radio receivers capable of participating in the global array. Others propose larger spacecraft with dedicated instruments designed specifically to observe black holes. If even one of these missions becomes operational, the improvement in our ability to see near the event horizon would be dramatic. Another promising development involves observing black holes at multiple wavelengths simultaneously. Right now, the Event Horizon Telescope focuses on millimeter wavelength radio light, but black holes emit radiation across the entire electromagnetic spectrum. They produce radio waves, infrared light, X-rays, and sometimes even gamma rays. Observing these wavelengths together allows scientists to build a more complete picture of the environment around the black hole. For example, while the radio image shows the structure of the accretion flow, X-ray observations reveal the hottest regions near the event horizon. Infrared observations provide information about dust and cooler gas farther out. Combining all these wavelengths allows scientists to understand how different layers of the accretion system interact. This multi-wavelength approach is already being used for M87 and the black hole at the centre of the Milky Way, but future instruments will make this technique more powerful. One of the next generation ideas involves pairing radio observations with gravitational wave detectors. Black holes produce gravitational waves when they merge or experience other dynamic events. While M87's black hole is not currently merging with another black hole, future observations may detect smaller objects falling into supermassive black holes. If gravitational wave detectors observe these events while telescopes simultaneously image the region around the event horizon, scientists could combine both signals to test gravity in unprecedented ways. This type of multi-messenger astronomy, using both light and gravitational waves, has already transformed our understanding of neutron stars. Applying it to black holes could reveal new physics. The future of black hole observation also includes improvements in computational power. The algorithms used to create images from interferometric data are improving rapidly. As computing power increases, these algorithms will become more capable of reconstructing fine details. They will also be better at incorporating physical models into the reconstruction process. Instead of simply converting raw data into an image, future algorithms might incorporate information about the plasma's behavior, the magnetic fields, and the expected shape of the photon ring. This could make future images sharper, cleaner, and more physically meaningful. Machine learning and artificial intelligence also play a role here. Researchers are already developing systems that can assist in reconstructing black hole images, identifying patterns in the data, and comparing observational results to simulations. These tools can accelerate analysis and reduce uncertainty. They can also identify subtle features in the data that might otherwise go unnoticed. As new instruments and methods emerge, scientists also expect to observe black holes over longer timescales. Right now, the Event Horizon Telescope captures static images, but black holes are active, changing objects. Gas clouds move, magnetic fields shift, hotspots orbit around the event horizon, jets fluctuate in brightness. By observing black holes repeatedly over months, years, or decades, scientists can create time-lapse sequences. These sequences would show how matter moves near the event horizon. They would reveal how black holes change over time. They would help answer questions about stability, variability, and long-term evolution. Another exciting direction involves observing entirely new black holes. So far, the Event Horizon Telescope has focused primarily on M87 and Sagittarius A, the black hole at the centre of the Milky Way. But the universe contains many other supermassive black holes, some of which may be excellent candidates for observation. Black holes with strong jets, clear lines of sight, or bright accretion flows could reveal different types of behaviour. Observing multiple black holes would allow scientists to compare them, identify patterns, and refine theories about how these objects form and evolve. Some black holes may have different spin rates, different environmental conditions, or different feeding patterns. These differences could reveal how black holes influence their galaxies and how galaxies influence their black holes. Each new target observed would add to the broader understanding of these massive objects. Future instruments may also allow scientists to observe the region inside the accretion disk more clearly. Right now, the bright emission from the disk blends with the light forming the ring. Higher frequency observations and improved resolution could separate these components, revealing the structure of the plasma and the patterns of motion within the disk. This would help scientists understand how matter spirals toward the event horizon, how magnetic fields twist, and how jets are launched. One of the more ambitious future directions involves using interferometry at even shorter wavelengths, infrared or optical. This would require entirely new technology, because the precision needed to synchronize optical telescopes across large distances is extremely demanding. But if this becomes possible, the resolution of images could increase dramatically. In theory, optical interferometry across Earth-sized baselines could produce resolutions far beyond anything currently achievable. Images of black holes would reveal even finer details, perhaps the structure of the photon ring, the shape of the space-time warp, or the motion of individual hotspots. This might sound like science fiction, but early experiments in optical interferometry have already begun. Instruments like the gravity interferometer at the Very Large Telescope have shown that extremely precise optical observations are possible when multiple telescopes work together. Applying similar methods on global scales remains a long-term goal, but one that scientists are actively exploring. Another future development involves improving our understanding of the environment around black holes through laboratory experiments. While we cannot replicate the extreme gravity of an event horizon, we can recreate similar plasma conditions, magnetic field interactions, and turbulence patterns in controlled settings. These experiments help refine simulations and make predictions more accurate. The combination of laboratory studies, simulations, and observational data creates a loop of understanding that strengthens theories over time. As you settle into this idea, imagine how many different pieces of technology, theory, and collaboration come together in the future of black hole observation. Each advancement builds on the last. Each improvement adds clarity. Each new observation reveals something previously hidden. What we see today in the image of M87 is only a small portion of what will eventually be possible. One of the most intriguing directions involves studying black holes not only as astrophysical objects, but also as tools for understanding fundamental physics. The extreme gravity near the event horizon allows scientists to test theories of quantum gravity, investigate the structure of spacetime, and explore questions about the nature of information. As instruments improve, these tests will become more precise. Observing slight deviations from relativity, if they exist, could provide clues about the deeper structure of the universe. Another path forward involves pairing black hole observations with cosmology. Black holes influence the distribution of matter in galaxies, but they may also play a role in shaping cosmic structure more broadly. Understanding how black holes grow and interact with their environments can help refine models of galaxy formation and evolution. Observing black holes across different eras of the universe, something possible with future telescopes, could reveal how their roles have changed over billions of years. All of these ideas converge toward a single expectation. The future contains more detail, more precision, and more depth than the past. The image of M87 was a beginning, not a conclusion. It opened a door. And now scientists are stepping through, exploring the room beyond with new lights, new tools, and new questions. As we move into the final stretch of this long, steady journey through M87 and everything it has shown us, there's a soft shift in the pace. Not a stop, not conclusion, but the kind of gradual slowing that happens when you've been walking for a long time and start to notice the world settling around you. The light changes, the air feels different, and the path ahead starts blending into the landscape in a way that makes you realize the walk isn't ending. It's simply becoming quieter. That's the kind of closing we approach now. A gentle one. A closing that leaves space for the story to keep going long after these words fade into the background. Throughout all the time we've spent exploring this black hole at the centre of M87, the story has looped outward from the edge of the event horizon, into the galaxy surrounding it, out into the universe, and back again into the details of light, matter, and gravity. And now, as we step into this final part, the focus drifts back toward the boundary that began this journey, the place where light is bent into a glowing ring, where space-time curves so deeply that even photons struggle to escape, and where the universe reveals both what we understand and what remains unknown. When you imagine standing near the edge of an event horizon, not literally, but as close as the laws of physics allow a mind to wander, the picture is never static. It's a region where time flows at a different pace than anywhere else, where matter spirals inward in constantly shifting patterns, where magnetic fields twist into shapes we're only beginning to understand, and where light orbits in fragile loops before breaking free. And even though we cannot physically approach such a place, it's remarkable that we've reached a point where we can observe it directly, interpret the signals it sends across space, and piece together a coherent story from those signals. The gentle closing begins with this recognition that everything we've learned about M87 was gathered from faint traces of light that travelled across millions of years and countless distances. Those photons had no intention of being observed. They simply moved outward, bent by gravity, heated by plasma, guided by magnetic fields, and eventually collected by telescopes scattered across the world. The fact that we can interpret them with such clarity is a quiet achievement. It's not dramatic. It's not full of spectacle. It's a product of patience, cooperation, and the steady accumulation of understanding. This patience is part of what defines the world of black hole observation. Unlike some areas of science where discoveries happen quickly, the study of black holes unfolds over decades. New instruments take years to design and build. New algorithms require careful testing. New theories grow slowly as observations refine what is possible. The work requires long stretches of waiting for the right weather, the right instrument alignment, the right orbital geometry for a satellite, or the right moment when the accretion flow brightens. And beneath that waiting is a deeper patience, the patience of light itself, crossing unimaginable distances to reach us at the exact moment our technology becomes capable of recording it. In a way, this patience reflects the nature of the universe. Everything that shapes it moves according to timescales much larger than our own. Stars live for billions of years. Galaxies rotate slowly, spreading their arms in arcs that last longer than the history of human civilization. Black holes grow and change over millions of years, not months or decades. When we observe M87, we are glimpsing a moment in a process that began long before we existed and will continue long after we are gone. That perspective doesn't diminish our role. Instead, it gives a sense of calm continuity. We are watching a universe that is patient enough to reveal itself slowly. The gentle closing also includes the understanding that much of what we have explored remains incomplete, and that this incompleteness is not a flaw to be solved immediately. It's a natural part of discovery. We've seen how M87 confirmed predictions from general relativity. We've seen how it revealed the behaviour of matter near the event horizon. We've seen how the structure of the jet reflects the black hole's rotation and the strength of the magnetic fields. But many questions remain. How exactly does the jet maintain its structure across such vast distances? What is the precise mechanism that accelerates particles to near-light speeds? How do turbulence, magnetic reconnection, and plasma interactions combine to shape the accretion flow? How does quantum gravity behave near the singularity? These unanswered questions don't create tension. They create space. Space for future researchers, future instruments, and future generations to continue exploring. The story of M87 isn't something that ends with an image or a single discovery. It's something that continues unfolding as new data emerges, as technology improves, and as theories evolve. Like a slow-growing tree, it adds rings over time, each layer building on the one before it. Another part of this quiet closing involves returning to the human side of the story. The image of M87 was created not by a single instrument, but by people. People who travelled to remote observatories, worked long nights troubleshooting equipment, wrote complex software, built algorithms from scratch, coordinated across continents and time zones, and collaborated with colleagues from countless backgrounds. People who brought their expertise, their patience, their curiosity, and their persistence. The image of the black hole became a symbol not only of astrophysics but of global cooperation. It reminded us that understanding the universe is something we do together. In the future, this cooperation will only deepen. More telescopes will join the network. Space-based observatories will expand our reach. Algorithms will sharpen their clarity. And new generations of scientists will inherit the tools, ideas and challenges left by those who came before them. The study of black holes is something that transcends personal accomplishments. It's a collective journey, a gradual expansion of knowledge that stretches across borders, cultures, and eras. As you relax into this idea, imagine the black hole itself, not as a dramatic Hollywood object, but as the calm, steady presence it truly is. It isn't roaring or tearing apart its surroundings. It isn't devouring matter in violent bursts every moment. Most of the time it simply exists, quietly shaping the space around it. The accretion flow brightens when gas falls inward. The jet pulses when magnetic fields twist or reconnect. But the black hole itself persists with the same consistency it has had for billions of years. There is something grounding in that, something steady. It reminds us that the universe doesn't require constant change to remain interesting. Sometimes the most fascinating objects are the quietest ones, the ones that reveal their secrets slowly and calmly, the ones that shape their environments not through noise or chaos, but through a gravitational presence so strong and stable that it becomes a reference point for everything around it. The gentle closing also involves recognizing that observing a black hole is not only a scientific act, but a reflective one. When we look at the shadow of M87, we are seeing the edge of a place where the known laws of physics meet the unknown. That boundary is not just a physical limit, it mirrors the way our own understanding works. We move forward step by step, learning what we can, acknowledging what we cannot yet explain, and gradually expanding the sphere of the known. The event horizon becomes a metaphor, not in a poetic or abstract sense, but in a grounded one. A recognition that even the most advanced instruments have limits, and that these limits guide future exploration. As you settle further into this closing, you might think about how the story of M87 affects the way we see the universe as a whole. It reminds us that even in the vastness of space, light finds its way across unimaginable distances. It reminds us that the universe leaves clues everywhere. Patterns in radiation, shifts in frequency, traces in magnetic fields, arcs in jet structures, and rings of light shaped by gravity. It reminds us that the universe is not silent. It is full of signals, waiting for instruments sensitive enough to detect them and minds patient enough to interpret them. It also reminds us that our place within the universe is not insignificant. We are small in physical size, and our lifetimes are short compared to cosmic timescales. Yet we have built tools that extend our senses across millions of light years. We have developed equations that describe the behaviour of space-time itself. We have created collaborations that span the entire globe. And we have taken the light from a distant galaxy and turned it into understanding. That ability is one of the quiet triumphs of our species. This final part of the journey with M87 also carries a sense of calm continuity. The black hole will continue shaping its galaxy long after these words are spoken. The jet will continue shining across space. The accretion flow will continue swirling. The ring of light will brighten and dim with the movement of gas, and future observers will continue gathering data, refining theories, and expanding what we know. The story of M87 is not one with a final chapter. It's a story that stretches into the future, always open-ended. As we drift toward the end of this narration, the outlook is peaceful. Nothing abrupt happens here. No sharp ending. No sudden shift. Just a soft settling, like the quiet after a long conversation. The universe continues on its own schedule, and we continue moving through it, learning at a pace that mirrors the slow drift of galaxies across the sky. You can picture the black hole now not as a distant threat or a frightening concept, but as a presence, a stable, grounded structure in the fabric of space-time, a place where gravity is strong enough to shape light into a glowing ring. A reminder that the universe contains extremes, but that these extremes can be understood with patience and collaboration. And as this story comes to rest at the edge of the event horizon, the calm remains. The journey doesn't end. It simply settles into the background, ready to be picked up again whenever curiosity returns, quiet, steady, and waiting in the glow of a distant galaxy.